Okay, okay. Yeah, you should tell me a little more. Are you going to talk about that
Yeah, well,
today
I mean,
or tomorrow?
tomorrow,
I'll be here.
but I, so do this
general
not too much about stories.
Right, right.
So we heard about the sequential deconformity.
Restriction of the families.
Describes as other. They can define
Right.
this.
Yeah.
Some extra.
Okay.
Right.
Right, I remember those, yes.
And recently, like
To do some.
4 years ago, we revamped this idea.
Okay,
And what we call now is the sequential deconfinement.
okay,
So then basically you can derive some assuming all those is cyber duality.
okay.
Procedure,
Yeah,
you
yeah.
deconfine and then you deconfine again. And
Right, right, right,
redefine.
right.
So.
But does it sort of ever come to a theory that is weakly coupled, you know, so, or, I mean, something, what I mean is, yeah, do you ever get like a phase where, you know, you sort of know what the dynamics is?
Well, I mean, in model where you have S-confined,
Right,
you
right.
can, you are.
Yeah, yeah, yeah. Oh, ESCOM, yeah,
But then you also have some self-duality cases,
Right,
and you
right.
also can prove them. using this
Okay.
technology.
So we were very unsure about those stuff. They're good.
That's exactly.
Good.
Yeah, I will say something about that. So, you know, this UST, this has 72 dual frames, and so all of them can be derived using all these systems.
Okay.
Yes.
No, I'm very interested.
No, no, just like that's
Very
what the
good.
community.
Thanks.
Your name is everywhere in my slide.
Thank
It's cool.
The generator.
It's not bad. It's like you, I think, a mistake, I think.
Csaba Opri is your student. Csaba,
Yes,
Opri tell him is your student, right?
he was my student, yes.
He's a postdoc now?
No, so now he is faculty at Hebrew University.
Oh, really?
He just started, yes.
I communicate with him from time to time.
And then he just moved back.
I see.
Okay, so first paper is the introduction or just share the fact.
No, you just try.
Okay, let's get started. So thank you very much to the organizers for doing this workshop on 50 years of supersymmetry. So I was trying to think back of my own career, how many years I have been thinking of supersymmetry. So I studied as a grad student with Lisa, and we were doing hadronic physics, B physics, and that kind of stuff. It was okay, but you know, at some point Lisa went to a workshop in Santa Barbara in 1994. And then she called me up from that workshop and said, by the time I get back, learn supersymmetry. So I bought a book of Wessenberger, and I got hooked ever since. It's 28 years, so it's more than half Okay, so I'm gonna sort of give a talk very much in the vein of what Hitoshi was giving yesterday. Trying to sort of use broken supersymmetry to try to learn something about strong dynamics and in particular about phases of QCD. And so, you know, we had an ongoing long collaboration with Hitoshi, my student Andrew, who is now going postdoc, and my former student Offrey, who is now a faculty at Hebrew University. And many of the works actually will be related on this yet to be published paper that we are doing with these guys. Some of them postdoc at Cornell, and Eric is in Hebrew University also, and Rick and Turin are in India. And then if I have time, I will also talk about the work with Hitoshi, Offrey, and Teruhiko. All right, very good. So again, you know, one of the most important questions, you know, is really to try to understand something more about the mechanism of confinement in QCD. And a lot of the QCD dynamics is actually encoded in the theta dependence of the vacuum energy, and also, you know, the potential for the eta prime. So this talk will be focusing on these particular aspects of QCD, how much we can actually learn about those by going into the supersymmetric version. You know, there we know how to study the strong dynamics, and then apply the method that Hitoshi was outlining yesterday, the method of AMSP, which is an UV insensitive, and, you know, in many cases, you know, pretty calculable method, at least for small perturbations. So that's going to be the goal for today. All right, so how did we get started about this? How did we get interested? Actually, you know, with these guys, we were really more interested in, you know, trying to understand the dynamics of axions and, you know, how exactly is the axion mass generated in QCD? Because we read all these papers and, you know, they draw these Tufts operators and they close up legs, and so we wanted to understand, you know, what you know, where does the axion mass actually come from, you know? So let me just tell you what the usual lore among phenomenologists is. Okay, so okay, we are starting, of course, with the theory. There you have the usual flavor symmetry, SUF cross SUF, broken to the diagonal, and there is an axial symmetry that is anomalous as usual. Under the axial, if you do an axial rotation, that will, of course, you know, give you an anomaly term, which is essentially shifting the theta parameter. And you have, you know, in the chiral Lagrangian description, you have a Goldstone boson matrix that has the usual pions, and the phase of the Goldstone boson matrix is the eta prime. And of course, under the axial rotation, because this would be the Goldstone boson corresponding to the axial symmetries, yes, the eta prime is going to be shifted in the same rotation. Okay, so the very naive assumption, and, you know, you can actually see this, you know, in, like, you know, the standard lecture notes that we teach our grad students from. We say that, oh, U1 is anomalous, it's broken by instantons, so instantons will give mass to the eta prime. So let's just go ahead and add the term that is sort of, you know, capturing the effect of instantons to the chiral Lagrangian. So if you look at, you know, some of the TASI notes on the strong CP problem, this is what we usually say. Okay, you know, makes sense. Yes, it's an explicit breaking term, and in terms of eta prime, it would give you an explicit potential to the eta prime. And it would be an instanton effect because there is an explicit e to the I theta in front of it. So we know that that is what instanton effects would generate for you. And it would give you an eta prime mass of order lambda. So that's, you know, what we usually expect. Again, on that term, just to be sure, you know, this term is the determinant. Is consistent with the Spurion analysis, so you can promote theta to be, you know, Spurion under the anomalous axial symmetry. And then, of course, this combined term with e to the minus I theta times that u is variant. And so that's what we usually say. So then we would say, okay, let's integrate out the eta prime, and the eta prime is going to adjust such that it essentially tries to cancel the theta dependence of the Lagrangian, the part that it can. But then there's an additional explicit breaking, which is the quark masses. Yes, so the quark masses are also providing you an explicit breaking. And the theta dependence comes back through the explicit breaking after the eta prime is integrated out and substituted by its mass. Okay. How does the so this would be the theta dependence after. So there's still pions in the system. Yes. So to get the true theta dependence of just the vacuum energy, you also have to integrate out the pions. And then you're going to get, for example, for the two-flavor QCD, yes, you're going to get the usual expression for the theta dependence of the QCD vacuum energy. Okay, so that for two flavors you can do this explicitly. For three flavors you have to do it numerically. Very good. Now, if you also had an axion, so that would be the kind of question that we were asking previously. That would mean that there's a separate additional anomalous U1 symmetry, a Petri-Quinn symmetry, under which the theta, you have to sort of, introduce another spurious symmetry under which the theta shifts. This n is, just whatever the anomaly is under the Petri-Quinn symmetry, and then the axion shifts by phi. And so that means essentially that wherever you see theta, you have to replace it by theta plus a. And then, so this would be Lagrangian. Yes. Now, the funny thing is that, many people are trying to give very complicated formulae or derivations for how to get the mass of the axion if you have F flavors. Actually, it's really, really easy. It's almost a one-liner because once you have the axion, yes, then it's very easy to minimize this potential, yes. The axion is just gonna adjust the theta dependence here, and the pion is going to be at 0. Yes, so that's going to be the minimum of this potential always. So you can just actually expand this expression to quadratic order and around it. And then the other thing is that, of course, you are only interested in the mass of the axion. You're not interested in the mass of the pion, So you're not going to try to invert to really solve all of these equations of motion. You just integrate it out, and the pions in terms of the axion fluctuation itself, and you get a very simple expression for the axion mass. And this is just a side note because this is something that you also see in many papers. People are writing long, song and dance about how to get, the axion in many flavors. So it's very easy. And it, of course, reproduces the expressions that everybody knows from a long time ago, from the 70s. All right, so that's the story that we usually use. Now, of course, the funny thing is that if you read Witten's paper from, I think, 77 or 78, his first sentence is, naively, you would think that you would add a determinant u into the chiral Lagrangian, but that's not actually what should be done. Yes? So he was looking at the larger limit of the theory, and of course, he realized that in the larger limit, the anomalies actually vanish, at least if the number of flavors is fixed. Yes? So actually, the eta prime mass should vanish in that limit when n is large. Now, if I go back to that naive term, yes, the one that is just the straight determinant u, yes, clearly it's not vanishing, yes. In that case, it's just eta prime, so it doesn't vanish for larger. And so Witten wrote this very beautiful paper. I think he was still a postdoc, like in the 70s, explaining that really the eta prime needs to go to 0 for many reasons. Yes, so it won't be able to cancel the theta dependence the theory in the presence of massless fermions if its mass doesn't go to zero. So its mass has to go to zero. It has to be actually, and not only has to go to zero, but he also estimated that it has to go like 1/n itself in order for it to be able to cancel the theta dependence once there are actual massless fermions introduced into the theory. So really, actually, the form of the potential of the term in the chiral Lagrangian that you're adding is expected to be more something like this, yes, where there is an extra 1/nth power in the determinant, yes, which also tells you something really important, yes, that this will not be an instanton effect, yes, because this term in the chiral Lagrangian is going to be e to the I theta over n, yes, and that's not an instanton effect, which, I mean, those who sort of know about QCD shouldn't be shocked, yes, because really, I mean, whatever is in the code of confinement is what is giving rise to these effects, yes, and we know it's not instant. So
But the instanton disappears in the limit of Lache.
well, so we'll talk about that also. But anyway, one of the questions that he immediately asked is that, oh, so this is a non-analytic function, yes, and how is it, if I write a term like this, yes, doesn't look like it's actually periodic in 2π periodic in theta. So how should I think of it? So what he said is, it's got to be then a function that has several branches. Yeah, so it's not just a function with a single branch. It's got to be a function with several branches. And as you move along with theta, yes, you are going to be jumping from one branch to the other branch. There will be phase transitions as you go from one branch to the other, and that's how you expect it. So here we have a little cartoon, for example, for pure QCD. If you look at this kind of potential, yes, you will have these 3 branches when n equals 3, and then you have the 3 cosines and the minima. The actual minimum of the theory is going to be this lower envelope of this potential. Yes, so you have to minimize. So you find the minimum in each branch, and then you pick the actual minimum between the branches, and that's what the minimum of the QCD potential will be. So it's going to be this lower envelope, and that's what the dynamics is suggesting for you that will actually happen. Very good. And then, once you have that, the eta prime itself is acting like a heavy axion, like a QCD scale axion. Yes, that's what it does. It's trying to cancel the theta dependence of the Lagrangian. Yes. So if there is no other explicit breaking, then it will actually relax to the minimum of the potential and cancel the theta dependence. Yes. So that's when there are no quark masses. As there is no explicit mass term, then the eta prime actually will just roll such that it cancels the theta dependence and will set to its minimum. Yes. Of course, if there are quark masses, then there will be, just like in the naive explanation, the theta dependence is going to come back through the dependence of the eta prime on theta. So the goal, after we understood this, so it's interesting. This is a very old story from the 70s. I have to admit I didn't really know about it, but we learned it. And so we wanted to go and check this in AMSB QCD. Of course, then we realized that we are not the first we will try to do that. Michael has been thinking about this already a few years ago. So he was doing similar things, but not with EMSB, but he was just adding as far as I remember, just soft breaking terms by hand, which is fine as long as for example, if the theory is weakly coupled, like we will see for the f less than n, then you will just get the right answers. Okay, but we tried to do it using AMSB. That was our task after understanding that this is probably the right thing. Okay, so just to remind you, Hitoshi gave a long introduction, so I I will only give you a one slide reminder about AMSB. Yes, so the important thing for us is that all the effects can be traced via the conformal compensator, which is going to get an F term. Yes, so this little m is the amount of supersymmetry breaking in the theory. And then you will have SUSY breaking effects from two sources. One will be in the scalar potential, and it will, we have an expression for a general Kähler and superpotential, what the effect will be. And then the other one, like Hitoshi explained yesterday, will be through the running. So you will get a gluino mass and spark mass. And as he emphasized, the really beautiful thing is that, of course, the spark masses are all going to be positive as long as the theory is asymptotically free. So exactly in the regime where F is less than 3n, you will get a positive spark mass. So the theory will, in some sense, at the very, very IR will look like QCD. Of course, it will still have squarks and gluinos in the dynamics. They will still be lighter. So what we describe is not true QCD, yes, because the squarks and the gluinos will still be participating in the dynamics. And in fact, many of the effects that we will see are going to be due to these quarks. But anyway, nevertheless, at least it's a theory where we can analyze and understand what is happening. Okay, so we first looked at the case when the number of flavors is less than the number of colors. So that's the Affleck-Dine-Seiberg superpotential case. And then, of course, we are also adding now a little bit of a quark mass matrix, yes, because we are trying to get as close as possible to ordinary QCD. So it will be a quark mass. And so we do what Hitoshi showed you. We add AMSB. So we are trying to get what the meson vests are going to be. You get this 1/m type behavior that we saw yesterday. And now the main new or different thing is that, of course, now we are actually trying to keep the Goldstone boson matrix, including specifically the eta prime, the phase of the Goldstone boson matrix. We are going to try to write down what exactly the potential that we are going to get here. Yes, so we will be very careful about keeping the phase of the Goldstone boson matrix and try to find, So, this is a theory where you can actually, derive the chiral Lagrangian. Yes. So it's a supersymmetric theory and it's in a controlled regime. So you can actually go ahead and derive the chiral Lagrangian. It's not the chiral Lagrangian of QCD because for that you would have to take little m to infinity. Yes, but okay, it is a chiral Lagrangian. And then out of this, so you see. So we are going to get exactly the kind of terms that Witten predicted. So there's the determinant u, yes, and you're going to get these fractional powers of determinant u, just like Witten predicted. The only difference is that it's not going to be a 1/n's power, but it's going to be a 1/n minus f's power. Okay, so actually introducing flavor is going to make a significant difference for the flavor structure of the theory. Yes, so that's the main difference. So you're going to get exactly the kind of cosine, these terms with cosines and various branches. So you have these 2 pi k. So the k is telling you which branch you are on. And the only difference is going to be compared to Witten is that you will get 1/n minus f.
Sorry, there were actually two papers, the Witten and the Veneziano. Now, Witten did the soft limit and Veneziano the Veneziano limit. So when you say you take the larger limit, you mean soft limit or Veneziano limit?
So here I didn't take any limit, yes.
But when you say 1/n minus f, it's not different than Witten because if f is fixed and n goes to infinity, then what I think what you want to say is that the natural combination in this approach is nc minus nf, right? That's what
we find, yes.
Right, okay.
So I don't know how, so I didn't know about the Veneziano paper, so I should read that one. So he took the large n large f limit. I knew that somebody must have done it, but I didn't know.
Yeah, the eta prime mass is actually nf/nc times.
Right, exactly. So that's what we will of course see,
So I think good in your approach, it's better to take the Veneziano limit.
Well, I mean, we want to, we want to check all possible limits. Yes.
Csaba, but I saw that in this supersymmetric way, it would be combination two terms in superpotential rather than potential. So when you're taking potential, it would be even a kind of crosstalk, right?
Right. So exactly. So just from the superpotential, you don't get anything because it's an absolute value squared. Yeah? So the phases drop out, but there will be cross terms.
Yeah.
A and B. You know, there will be these terms that Hitoshi also mentioned. These terms that are just just direct SUSY breaking contributions, from that are proportional to the potential, to the superpotential, but show up directly in the potential, in the scale. So these terms, right? So both of those will be present. Yes, very good.
I also have a question related to this.
Yes.
Concept.
Yeah.
If you're not taking the Cordova, Theta prime should have a mass which is order 1 because of the chiral anomaly.
Right.
So you would normally not expect it to be part of the chiral lemma if you don't take it.
Right. So exactly. So it's exactly it's heavier than the other pions. So absolutely. Yeah. So this is
seen in your okay, good. That's
exactly. So we do get the eta prime mass that is of the order of of lambda. Exactly. It's not really part of the chiral Lagrangian. So you really want to integrate it out. Yes, and then so that's okay. Very good. So we took then several different kind of limits. Yes. So we looked for pure QCD. Yes. So then it's exactly, the 1/n, like what we predicted. Also, Michael found that for small number of flavors. Yeah, so that's like, taking the large n but small f, keeping f fixed. Also, the eta prime mass goes like 1/n. So,
but it is still proportional to original quark masses, right? Because you are going for eta prime about the lambda square. Right?
So the eta prime mass is not proportional to the quark mass.
Right. Here you
Little
have
m is the SUSY breaking. Little m is SUSY breaking. Yes.
I see.
Little m is SUSY breaking.
I see.
It's not proportional.
Sorry, I'm a little bit confused about the n counting importance of that. So f(phi) squared goes like n, right?
Right.
But then if I take a Veneziano limit, which I in principle am allowed to do, then f is number of flavors. So it looks like m eta squared will go like nc if it's n limit.
Right. I will have that. I don't remember. Okay, here. This is the limit I think that you're asking. Yes. So this is okay. So another interesting cases when f is of the order of n. Yes. So both of them go to infinity separate together. Yes. One interesting example is the f is fixed to be n-1. The reason why this is an interesting example is because in this case you actually don't get any branches. Yes, because it's not shocking. Yes, we know that in that case the ADS superpotential is actually an instanton effect. Yes, when f equals n-1. So you do expect that it's just straight e to the I theta. Yes, and in fact that's what you find. And in that case, the eta prime mass doesn't go to 0. And if we did this properly, it looks like it goes like n squared.
That doesn't agree with Veneziano limit.
Yeah, that doesn't seem right.
Yeah, Veneziano is an f over nc, which
general,
goes to 1.
It should just be around
Yeah, the mass of an open string should be order 1. It cannot be order n squared.
Okay, so we'll,
No, it's more in this limit. So it is more like a glue ball or a closed string because it's a flavor
That
singlet.
shouldn't go like n squared.
Sure. Yeah. It should go like 1. It should go like 1 because it's like a closed string,
Yeah.
because it's a flavor singlet. So it mixes in the Veneziano limit, the eta prime mixes with glue balls. That should be order 1.
Yeah, no, but remember you started from the point that the large limit m eta prime goes to 0, right?
right. But again, this is larger
Not in
and
the
larger.
Veneziano limit. Yes. Arcadi.
Sorry?
In Veneziano limit. it
So
does not-
okay,
No,
think
but
about it. We were not
like,
sure.
again,
That's good.
I think there are funky things in the ADS. If you take the larger limit of the ADS superpotential, it's funky because of this runaway. So it might be.
but again, it's not really runaway. It is stabilized by some.
I understand. There's something funky before you deform it.
Actually, in your first formula, the one where you have n going to infinity with nf fixed,
Right.
it already doesn't look right because it looks like it's nf squared over n instead of nf. So that's not what one would normally expect. It's about times. Already that's. I suspect there's something funny about the version.
Still have some work to do before we publish this.
No, and in the real QCD, we know that theta prime, I mean, is a lot of lambda, but not enhanced, right? I mean,
Right, but n equals f, so.
Yeah.
So,
yeah, no, okay.
Anyway, so what I want to also say is that so what I want to emphasize is for n minus f is not one, it's not an instanton effect, just like we expected it. Of course, we know what it is. It's Gaugino condensation. Yes, that's what the dynamics is that is giving rise. So we shouldn't be surprised that we get these branches, and the origin of the branches is just this. The 1/n minus f's root that is showing up in the Gaugino condensation. But for this special case, it is an instanton effect and no branches. Eta prime mass does not vanish for large n. And of course, again, it's not surprising because the anomaly doesn't vanish. Which one is QCD? Of course, we don't really know. We did look at the other cases, f equals n. And f equals n plus 1. So actually, the analysis with the MSB is relatively straightforward. We had to make the assumption that we are on the branch that has the usual chiral symmetry breaking, which for f equals n, we are, may only be a local minimum. We don't really know, but leaving that aside, you can go ahead and relatively simply calculate, again, the eta prime potential. And again, what we find is for f equals n and also for f equals n plus 1, there are no branches. So it looks like an instanton effect, but you don't really know what instanton. The whole thing is strongly coupled. So, maybe it's an instanton dual gauge, or and then for f greater than n plus 1, actually the analysis becomes very simple again. There will be a cyber dual, yes, but along the direction where you have the right chiral symmetry breaking, the dual quarks are going to pick up a mass. You can integrate them out, and there will be a Gaugino condensation in the dual gauge group, and it will have essentially the same kind of structure as the ADS superpotential, except f and n are going to be replaced. So now there will be f minus n branches instead of n minus f branches. Okay. And so that's going to be the story here. All right, so I think I'm running out of time, so I'm not going to say a lot more. There was another work that I wanted to talk about. That's it, Hitoshi, Offrey, and so there we looked at the theta dependence of perturbing theories in a different way. So we just started with pure Seiberg-Witten n equals 2 theories. In that case, there is no eta prime, so that's actually a really nice way to get directly to the theta dependence of the theory without sort of having it washed out by an eta prime that is then going to adjust and cancel some of the theta dependence. And of course, Konishi did actually essentially the case without flavor he already did, just not using the MSB, but that's fine. Essentially the same results. And so we redid that, and we found the interesting stories. You have the different monopoles or dions becoming massless at the singularities, and once you perturb it with the MSB, the story will always be, of course, that you will be getting stuck at some of the singularities, and those monopoles or dions are going to converge. That's what's going to give you the theta dependence, so which is going to give you the plots. So this is the case with zero flavor. Also, as I said, Konishi already had this in 20 years ago, so whatever, 25 years ago, yes. So you have here the nice phase transition, and then for f equals 1, the only surprising thing is that we are starting to get phase transitions at values that are different in theta than what you would have thought without flavors. So here you're going to get it at pi, 2 pi, and then for 2 flavors, 3 half pi, and for 3 flavors, that's the most weird one. So you will get this potential here. It's partly flat, but then partly viscous. All right. Let me try to summarize. Again, soft liberating SUSY is a very nice lab for studying confinement. AMSB is a pretty nice tool, and because it's UV insensitive, and it's only sensitive to the scaling properties of the various parameters. Eta prime potential and the theta dependence are some of the best hints for what happens for confinement in these theories. And we studied n equals 1 SUSY QCD and VDMSB. We found the eta prime potential is branched and it has these n minus f absolute value branches. In some unusual cases, when n minus f is equal to 0 or 1, it will be an instanton effect. Otherwise, it's a gaugino condensation either in the electric group or in the dual group. And then this is the part that I didn't have much time to talk about. So for the n equals 2 case, we will always get condensation of monopoles of ions. We get also a branch structure in theta, but it's also flavor dependent. This was all SU2 only. All right, thank you very much.
So in the cases where an F is larger than an C,
Yes.
you have the Seiberg dual. So it makes, I guess, sense just to calculate the eta prime mass using the magnetic dual, because then the meson
That's
is.
what I did. So,
Yeah,
sorry.
okay, maybe that's when I.
That was too
When I
fast.
took water.
Yeah, I was starting to run out of time. Yes. So exactly. So
Oh, yeah, I saw that, but I didn't.
So we had the Seiberg dual.
Yes,
And then, we have the meson picking up a wave, yes, along the mesonic direction, then the dual quarks are going to be massive. So
right.
you integrate out the dual quarks and you essentially get, just the dual gauge group and gaugino condensation in the dual gauge group. So an SUF minus N gaugino condensation, and then so that's how you get the F minus N various branches.
No, I'm asking specifically the eta prime mass in this approach.
Oh.
That's what I meant, to
Oh, the
calculate
mass
the
itself.
eta prime meson
So-
mass
so
using
here-
the magnetic dual.
Right, so here is the potential. Here's the potential, but I didn't write down the formula bit in terms of N and F. Yes, so we should. Yeah, but here is the full potential. Yeah, so you see so this is the potential with eta prime and the ions are still in.
And you're saying it's essentially the same as
It's essentially the same as the SU. It's just N minus F is replaced by F minus.
Thanks.
Yes, Michael.
Yeah, so could you say one or two about what anomaly deviation is doing for you as opposed to just introducing some?
So I think for the case of the F less than N, I think our analyses are equivalent. Yes. For the case of F equals N and greater, I don't know. I mean, it allows you to map precisely, the SUSY breaking through the strong dynamics essentially. So I don't know. I mean, I don't know how I would analyze the F equals N or N plus 1 or higher cases without AMSB, yes, or without at least not just by I mean, there may be other methods, but you need some way of mapping the SUSY breakings through the strong dynamics, yes, through the duality. I'm not saying that's the only way to do it, but that's why it.
No, it seems to me that no, I mean, when you're saying that it's not instant effect, I mean, I agree that in terms of the dependence and all the stuff, but in this supersymmetric consideration, I would say that kind of in the beginning it is still instant effect, but then when you're going to this other cases, not F equal n minus 1, it kind of appearance of gluing condensation associated with existence of instanton before, so it became more complicated. So to say no.
So that's the question, yes? I mean, it's not a direct instanton.
Right,
effect in the
this I agree,
potential,
right,
yes.
but in certain way, instanton
Is
was
do instantons cause gaugino condensation?
no,
So
no, the incident was the example that U1 is broken. I mean, right, and then indeed, I mean, there are these
right.
different levels.
Right, so the question really is, what is the actual dynamics?
Yeah,
that gives rise to
but
gaugino?
I trying to say that you can trace it back to existence of non-perturbative F like instanton, but of course, for say F not equal n minus 1, you should do few steps more.
Right, so exactly, so in SUSY, we know because of SUSY, what it is, yes, but even there, the true origin of the gaugino condensate is not totally clear, yes. So, I mean, like I guess Eric is thinking about it.
There will be talk about.
Right. So yeah, all right. Thank you so much.
Supposed to be this computer.
Oh, I still have connected, yes.
Ah. Connect.
Right, but there is change. Should be doing something.
Yes.
So,
That you wanted in full screen presentation.
Okay. Our next speaker, I'm substituting Zoka for a moment, is Armoni, and he's talking about S-Duality for Maxwell Chern-Simons theory.
Thank you, Arkady. Yes, great pleasure to be here.
I did not mention that you are from Swansea.
That's also true. I'm a Welsh physicist. So yeah, thank you, Arkady. It's great to be here again. Last year, maybe next year again. And my talk is indeed about a recent paper finding the S-dual of Maxwell Chern-Simons theory. It is based on this recent paper. My talk is based also on the paper of Deser and Csaki. It's an extension of their work, and sadly Stanley Deser passed away recently, so I dedicate this talk to his memory. So let's start with the start of the maybe 19th century. Well, S-duality is not 19th century. It's a duality between n equal 4 superunions theories, but in the abelian case, for the U1 case, it reduces to the standard Maxwell electromagnetic duality that swaps F and F star. That was, I think, was known to Maxwell. It was known classically at the 19th century, I guess, that without sources we have this symmetry in Maxwell equations. In 3D, it is also well known that Maxwell theory is S-dual to a real compact scalar. So I denote 3D quantities with small letters, so small f is dual to star d5. And then the question is, the natural question that I would like to answer today is what is the S-dual of 3D Maxwell theory when we add a Chern-Simons term? Now, when I prepared this talk, I mean, I had this talk with for string theory, so it included some string theory, and then I erased all string theory from this talk because it's Minnesota. So I thought the audience here will not like so much string theory, but I was mistaken because I see that in the audience there are people who are interested in string theory. So essentially, I will rephrase the same question in terms of string theory. Suppose that we have this brane configuration, that's the electric brane configuration, and it is well known that on this brane configuration lives Maxwell Chern-Simons, and then this is type 2b, so we have S-Duality, then S becomes a D5, this is the minus k comma 1, and this is a D3, and essentially this is Maxwell Chern-Simons that lives here, and the question is what lives on this brane configuration, and there are some claims in the literature, and they are not correct. I will comment on it. There were several attempts. If I knew the answer in terms of the branes, what happens here at low energy, I would automatically know the answer. It's not so easy in terms of branes, but but the talk is a field theory analysis, and that it will tell, and then I will answer the question in terms of the branes. So I will answer at the end of the talk what lives on this brane configuration. Okay. So let me review a bit the dynamics of Maxwell Chern-Simons theory. This is Lagrangian. It's better to write the action of the partition function to get something well defined, but you know what I mean. So that's the Lagrangian. And what is this theory? It's a free theory. It's a simple theory. We have a vector Melton of mass. This is the mass of the vector boson. And what happens is that when we go to lower energies, the kinetic term is irrelevant, and the theory flows to a pure level Chern-Simons theory. And as we shall see later, this theory admits a global ZK one-form symmetry, and the generator I will show this is the generator of the one-form ZK symmetry. This discrete one-form symmetry is spontaneously broken if the theory is compactified on the torus, and we get the generated bucket. So these are known results in Maxwell Chern-Simons theory. Oh, I'm not sure if someone constructed that, but I will show how to. I will derive it. So in the past, there were several proposal discussions. What is the S-dual of Maxwell Chern-Simons theory? And Desiree and Csaki almost got it right. So they were close. What do they argue? They argue that they know the dual of the theory at the quantum level, and their theory, their proposal is almost correct. It contains a massive vector, but that's it. It doesn't contain any Chern-Simons term, and the theory essentially flows to nothing at lower energy. So it's just a massive vector, their theory. And such a theory cannot be the full answer. It doesn't make sense because as we saw, the Maxwell Chern-Simons theory flows to pure Chern-Simons, and there is a rich vacuum structure because of the Chern-Simons theory. And this theory that they propose flows to nothing because of the mass gap, and that's it. It leaves nothing behind.
No, but
so the self-dual model of
you have k sectors of the theory because you have the general vacuum, right? So
yes.
The question would be, what is a ground state of the theory when you have the general vacuum?
Yes.
So in spite of the fact that there's a gap, right?
Yeah.
You still
exactly. That's the dynamics of Maxwell Chern-Simons. What they propose is something called self-dual model, and it doesn't have all this rich structure. Yeah. So that's the problem. Now, another claim that appears in the literature that is not correct, which is separately, is that if we have a U1 level Chern-Simons theory, then under S-duality you get Chern-Simons theory with a level -1/k that appeared long ago in the literature, and that doesn't make sense because we cannot have a fractional Chern-Simons term even in the ability. Now, a partial answer to the question I'm asking was given by Gayotto and Witten. So what they wrote is correct. This is the Gayotto-Witten partition function, and what they say is that the S-dual of Chern-Simons theory is that. In terms of the brane configuration, essentially what they answered is what happens if you take this d5 to infinity. So it's part of the answer. So that has to be part of the answer. Okay.
I think this is called the S transformation of Witten. It's something from 2003, much before.
Around that time.
Much before the
This is taken from a paper with Gayotto about boundary condition, what happens under S-duality to boundary conditions, etc. So now, of course, if you naively integrate out C, then you get -1/k Chern-Simons. But this integration is subtle, and it's wrong to do it in it's wrong just to do it kind of classically and to write -1/k. It's just wrong. It's not good work.
We can write many larger level matrices, which also are equivalent to U1 level K. Is there something special about having this additional one gauge field?
It's a way to write the S-dual.
What do you mean by
That's what
S-dual? What do you mean by S-dual?
So in string theory, it is perfectly well defined. This is why I bother to write it. It's the theory that lives here. So that's the S-dual. That's what I mean in terms of and that's, I think, unique. There's no ambiguity about the Gayotto-Witten.
But from a field theory point of view, you're just trying to write something else that flows to U1K.
So I'll explain exactly what I'm doing in field theory, but essentially I will, to make it well defined, I embedded it in type 2-based S-duality. So I want actually to tell you what lives here. We'll see. And I will make several checks and try to convince you that it's correct. Yes.
Can I just, following up on Clay's question a little bit, is there any smaller context than string theory in which you can
we'll see.
Pose this question? Like, you know.
I will see. Okay. Let's see. So it's for sure. I'm proposing a dual. I call it S-dual, and it's another theory that is equivalent, and the name S-dual is borrowed from type 2-based S-duality. Okay. Let's see. Let me move on. We'll see, and then we'll discuss. Okay. Right. So let me explain what I'm doing. So let me first review how we get S-duality or electric magnetic duality in the standard Maxwell theory. We start with something people call often a master field, and that's the master field, what you see. And how do we get the S-duality from this master field? So it's if we integrate first over Fm, and Fm is a gauge invariant 2 form, then we get the electric theory, the 4D Maxwell theory, right? Now, if instead we integrate over AE, then we get this partition function, and then of course we can write F, the gauge invariant 2 form. I mean, we have to write it as DAM, and then we get the magnetic theory. So that's why the master field is useful to generate the standard electric magnetic duality of Maxwell theory. And what we see is that the coupling G is replaced by the coupling 1/G. So what I will do, and that's again, it's inspired by the brane configuration. So what do we have here? We have Maxwell Chern-Simons living on this brane configuration, but essentially what it tells us is that we have an n=4 theory with some boundary conditions, and that's it. And what I want to answer is what happens for the 4-dimensional theory when we define the 4-dimensional theory on an interval with some boundary conditions. What happens under S-duality? That's what I will answer.
So the new question here is what happens when there is a kinetic term on the boundary?
Yeah, it's, I will answer everything. You will see. So let's do the dimensional reduction. So we have a 4D2 form Fm, and under dimensional reduction, we have a 3D2 form small fm, and a 1 form Am. And the 4D gauge field Ae becomes a 3D gauge field Ae, and a scalar phi. Now, the 2 form Fm and the scalar phi e decouple from the rest of the action and the partition function. So essentially, the partition function, there is a sector that I'm not interested in. It's like kind of the standard duality between this Fm and phi e, and that's I'm not interested in that. So what I'm interested in, or the result of what I said, is that I propose the following master partition. So now this is the master partition function, which is relevant to the problem that I'm discussing. So we have Am and Ae. Am is gauge invariant 1 form, because it's a dimensional reduction of the gauge invariant 2 form from 4D. So we have to remember that, and that's the term for the Am. And I added by hand Chern-Simons term. I could start in 4D with a Chern-Simons term simply by, I mean, it lives here, so it's like, well, it lives here. There are various ways to argue why there is a Chern-Simons term. So anyways, I'm just proposing that. I could have started my talk with this partition function, but I want to relate it to the brain configuration. So, right, so if we integrate Am, which is gauge invariant, there is no problem to integrate it out, then we get Maxwell Chern-Simons. So it makes sense that this is the master partition function. It just recovers the electric side. So that's what lives on this brain configuration. And now I can integrate out, I mean, I can try to integrate out Ae to get the S2. So let's discuss actually 2 special cases. So if I add, suppose that I just substitute k equals 0 in this master partition function, then I get that. And if I get that and integrate Ae, then I get the Bianchi identity. I get that I get that I can write Am as some d phi. And then I recover the standard duality for when k equals 0 between Maxwell theory and a compact scalar. So that's what lives on this brane configuration when k is 0. When k is 0, we have 2 parallel NS5 branes, and the S-dual is 2 parallel D5 branes, and that appeared in Hanani-Witten like more than 20 years ago. So Hanani-Witten told us that the standard duality between Maxwell, pure Maxwell, and a compact scalar is simply we can recover it from S-duality in type 2b if we put 2 parallel NS5 branes, and that's the case when k equals 0. Another case is to take g squared to 0. G squared to 0, the 3g squared to 0, is essentially to remove the NS5 brane and the D5 branes, and that's Gayotto-Witten. So then I need to recover Gayotto-Witten, and indeed, when g squared equals 0, my master partition function reduces to the Gayotto-Witten partition function. So my proposal passes these 2 cases which were solved previously. So that's good. So my proposal is compatible with the existing literature. So now in principle, I need to integrate out Ae, but it's a bit tricky. So what I will do something else. And I will just rewrite it in a different way by changing variables from Ae to B. So I'm just writing it in this way. And what we see is that by changing variables, which is okay because this is gauge invariant AM, so I can do things like that. It doesn't cause any problem. Then I get this partition function, which is interesting because then I decouple this part from this part. So what I get is a product of the Desert-Jakiv theory, which is this part. That was the original Desert-Jakiv theory, accompanied by a pure Chern-Simons theory. So essentially, my proposal is simple. Maxwell Chern-Simons theory contains two sectors that don't talk to each other. One is a massive vector, and that's the Desert-Jakiv, that's recovered by the Desert-Jakiv theory. But then there's also a term, which is the pure Chern-Simons, which is actually kind of a singlet of the S-duality. It remains the same, right? Not 1/k and not nothing. We can write the answer is a product of two things. One captures the topological properties, and one is just like a silly massive vector that doesn't carry any. So that's actually a property of Maxwell Chern-Simons theory. It's kind of mixed in the variables of Maxwell Chern-Simons theory, but we can rewrite it differently. And then the dynamics is more manifest in these variables.
Can you just elaborate a little bit? I think you said it, but why that change of variables was globally well defined?
Yes, because the AM was is gauge invariant, so
AM is
it
gauge.
transforms.
Is AM also flat?
No. So, but it transforms both sides of the equation transforms the same way.
But
So they are okay.
the fluxes of little AE and little B are both 2 pi.
I think so. I think
Even though there's
it's
a
fine. If you calculate the
AM is not the gauge field.
AM is not a
real
gauge.
one.
AM is not a gauge
It's not a
field.
gauge field.
So
So you don't have constraints on its flux. Flux is 0.
The flux is 0 for AM. That's what
It's not a gauge.
yeah, that's the idea. So so then I can write the explicit map, how to relate it. By the way, how much time do I have?
You have 7 more minutes and then 5 minutes for questions.
Oh, okay. That's okay, because essentially that's well, I have things, but it's essentially the main thing I wanted to present. So I know the map. So I can go from the electric to the magnetic. It's just a change of variables. So I found the explicit map between the two theories. Right. So just few things. First of all, that's not about the duality. It's just I promised to say what is this one form ZK symmetry. So essentially, suppose that I wanted to calculate how many strings or Wilson loops pass through this area. So I can construct an operator, let's call it G, in such a way that it counts how many mathematical strings pinch the surface. And the way to construct it is to write the equation of motion of Maxwell Chern-Simons. This is the equation of motion. I can integrate both sides of the equation, and in this way I can construct this operator G, the generator of the ZK one form symmetry. That's the explicit form. And what is nice is that in terms using the map that I showed, if I write it in terms of the magnetic variables, it's just B. So it's just, which is natural because B is the variable that captures the topological properties of the theory. So it's just a useful map because it factorizes the kind of massive part and the topological part. So G, like writing it in terms of the magnetic side is this. And what else? Just other things that I can say about the map. And so, for example, because just to write a partition function is not very interesting. I want to calculate, let's say, Wilson loops in one side and magnetic loops in the other side. So, for example, I can put here fundamental string FF bar that will create like charges on the world volume of the D3. So this is a Wilson loop, a rectangular Wilson loop that maps to a PD bar, D1 bar in the magnetic side. So I want to know what is this creature, the rectangular Hopf loop, let's say, call it, or magnetic loop. It's not exactly a Hopf loop. So we see that the Wilson loop in the electric side is mapped to this this loop in the magnetic side.
Does the 2 pi k over 2 pi divided by k times AM, is that ever non-trivial? Can I just erase that and get a correct question? You said it's not a gauge field. Can I have Armoni? The AM have Armoni.
Whether it contributes,
Yeah, but does it ever contribute?
maybe it doesn't. I haven't thought about it. Maybe it doesn't. Now I can start with a magnetic loop in the electric side and use the change of variables. And it turns out that both are trivial. And from the brain configuration point of view, it's simple to see that if I start with a DD bar, the D can end on an NS5 ring. So if I have something like DD bar, in order to minimize the energy, they would prefer to end here. And the same as fundamental string ending on the D5. So in both sides, I will not get anything. And that was confirmed a long time ago in field theory by Csaki, by Sunny Csaki. So he wrote a paper, field theory paper about Maxwell Chern-Simons, and he found that the magnetic loop in the electric side is trivial, and then we can verify that under the map, the magnetic loop, the Wilson loop in the magnetic theory is also trivial. Right, a few comments about going beyond the free theory. We can add fermions, and this is the partition function of what I called quantum electrodynamics Chern-Simons with the NF fermions. And then since I know the explicit map, I can construct the magnetic dual because I know the map. So I can do that. Another thing I can do, which is non-trivial, is to put multiple D3s and to ask what's happening to the non-abelian theory. Then it's becoming like maybe more interesting. And essentially the answer is that it works. It works the same way, except that the magnetic theory, so this is the master, and I can use same like change of variables, but you see this is a non-abelian Max Yang-Mills Chern-Simons, and under the map I will get something similar to what I will get two sectors, but this time they talk to each other. So there is a topological sector, there is a theory with a mass gap, but they interact with each other. So there is no decoupling in the non-abelian.
Right, how do you even, I mean, even before adding Chern-Simons, I mean, what do you mean doing this sort of dualization for non-abelian theories?
For the non-abelian?
You cannot even dualize the vector on scale, right? Let alone Chern-Simons. How do you do this dualization? Like, it would be like doing Kapustin-Strassler, but non-abelian.
Yes. That's the master. So this is
important that there is Chern-Simons, just to understand. If you don't have Chern-Simons, you cannot do that. I mean, I'm just trying to understand your claim. It's crucial that you have a Chern-Simons.
It's in a sense probably easier, but it's interesting to check what happens in the limit when I eliminate K. Yeah, I think it's not known. it's mirror symmetry, and the non-abelian case is difficult, but now in a sense it's easier because there is a mass gap.
Yeah.
So when you have, in a sense, what you're asking is what happens with for multiple D3 branes between the two D5s, and no one knows the answer. But in this case, it's easier. When the brain is tilted, it creates a mass gap, and it's easier. So what we learn, this is the master partition function that I propose. If we integrate the magnetic variable, you recover the electric theory, then you can do the same trick. You get the same thing. Everything goes through. You get something similar to what I got in the abelian case. However, now the Chern-Simons and the massive theory interact. So I think I finished. So that's my conclusions, and that's it. So thank you very much.
The non-abelian case is AM gauge invariant.
AM is a gauge invariant.
The middle term that you have there, is that doesn't the field strength transform?
AM is transforming like homogeneous. It doesn't have the inhomogeneous piece.
So AM is not.
No, but it only has the homogeneous piece.
I see what you are asking.
So it's in sense, it's not gauge invariance, right?
Yes, so
Like a vector Pausan that the color
Yeah.
are joined, but no.
Yeah,
But no gauge transformation.
But then it's not a gauge theory.
it's not a gauge theory, and it will not get, but it's not a singlet either, if that's your question.
That was my question.
But it's not a singlet.
It's following this.
It's
In pure Maxwell theory, Billion duality is really useful because, for example, you can use it to say something like confinement, so on. You have some vision for what we can learn now that you've derived this duality that we didn't know, or that would be easier to understand in this language.
I waited for this question because it's like when undergrads ask me about theoretical physics and what's the use of it. And I have a quote from Feynman. So Feynman said, theoretical physics, that's surely it has some applications, but it's like sex. That's not the reason we do it, right? Yeah.
So in that the abelian case at the very beginning, so you mentioned 1/k Chern-Simons because it's defined. I agree with that. But that roughly corresponds to fraction of Monopole effect.
Right. So the condensed matter physicists sometimes do that.
That's exactly what you wrote.
But they are criminals.
Exactly what you wrote.
But that's a crime. So the Gayotto-Witten is well defined.
Yeah,
And
that's what I mean.
So what they mean is actually Gayotto-Witten. That's well defined. -1/k, you can write it, but it is not correct. So the right thing to do is Gayotto-Witten.
Okay, so that's a right way to talk about fraction of
And
Monopole.
naively, if you do a naive integration, you get -1/k. But when I say naive, it's actually wrong. It's the wrong integration.
Fractional Monopole effect is for a background field, not a dynamical field. So it's a different thing.
That's when A would be frozen.
Yeah.
A would be
Something
frozen.
different, fractional Monopole. It's for a background field.
So then you are saying we can still use this theory. It's kind of
something else.
okay.
Yeah. I mean, what you did is more similar to Son's theory of the half feeling. Now there is coffee break. Thank you. Am I supposed to email?
Wish.
Or I can.
That will be.
Who did you email it to?
So do this.
Right after
Yeah.
I need to be paid allowance for that, but I have the meeting.
Oh, you have a meeting and that, oh, yeah, you told
You can try to upload it yourself. Everything.
But it's better to send her.
But this time I probably have to take Uber.
Right.
There isn't a different thing. It's like you have in the usual formulation, you have a massive closer and a Chern-Simons center.
Yes.
In
And
the
here they
usual,
decouple.
in the usual formulation, they are like the same variables.
Yeah.
Okay.
And what I did, I
Now,
decoupled them.
if you decouple them, it actually the application is also in the non-abelian case, all you do is basically decouple them. Now, the reason that it's useful is, for instance, there is this idea that it's ladder fields. You couple ladder fields to pure Chern-Simons, you get one answer. Couple ladder fields to Yang-Mills, that's Chern-Simons, you might get a different answer. That's the story about QCD-3. So by decoupling them, you can see like the coupling to the massive boson maybe gives you some effect. And the coupling to the Chern-Simons might give you the CFD kind of CFD, and you'll be able to disentangle this. You could understand why the coupling works. Yang-Mills Chern-Simons gives a different answer from the coupling of ladder fields to pure Chern-Simons. So this is the use of decoupling of these two factors. That's why I think the application of your.
Yeah, I haven't thought about it.
But that's like, I mean, decoupling, you remember the whole idea that when you couple to Yang-Mills Chern-Simons, because the theory is already strongly coupled at the scale of the massive vector boson, you cannot really say that it's the same as coupling matter to pure Chern.
Oh, you mean in essentially offers question
Yeah.
about the thing you did,
Yeah,
like the
because-
contradiction, what you did with.
Yeah, because
Minimal.
you could say that already at the scale of the massive vector boson, the coupling is strong. And you integrate out the vector boson, and you get not just matter plus Chern-Simons, you get matter plus Chern-Simons plus a lot of crap. So it might flow to a different fixed point, or might be not even a fixed point. It might be in a runaway, it might be in symmetry breaking phase, but it might not be in the second order transition.
Yeah,
So by decoupling these two sectors, that's the application of what you're doing.
That's one possible application.
It's not a
Yes.
duality,
Some
it's just a way to decouple the English questions.
It's a change of variables, but it doesn't.
No,
Yeah,
but-
my motivation was different, but
No, but by decoupling the massive vector boson from the Chern-Simons theory, it has this application. But it's not a duality. It's just a decoupling, it's just the variables that.
that's S-Duality.
No, but it's just a set of variables for which the massive vector.
That's
boson and Chern-Simons are not talking. to
That's
each
the
other.
outcome of S-Duality.
No, I mean, it's just semantics, but
I know.
If there is
They're
a-
very, yeah, it's semantics.
But if there is an application to this idea, it's gonna be to understand why it deflects the RG flow when you
Yeah,
couple to
that-
the massive vector boson.
I haven't thought about it. We can like try to work out
Yes.
some details related
Yeah.
to our
Yeah,
paper
you
and
can
the
just
paper, the
couple,
question of.
let's say you
Theta.
couple fermions, massless fermions, and you can try to actually now using your formalism to
Yes.
integrate out the massive vector boson.
Yeah.
It might induce some quartics, and that's why you're not the same point.
Yes.
I was thinking about this Cardi formula that was presented by Kenichi yesterday.
Yes.
I'm still very confused by the following. So there are various papers, and you wrote some, in which one tries to obtain this Cardi formula, this high temperature expansion. And for instance, now you notice that if you are on the first sheet or you are on the second sheet, then different expressions. And the second sheet is more robust. In the first sheet, it's there are subtleties. Sometimes you can compute it, sometimes not. How is it possible that actually there is there's one formula with one coefficient? Does it reproduce everything?
Yeah, I think the answer is yes. So you basically reduce the theory in a circle.
Yes.
You get 3D theory.
Yes.
This 3D theory can have one vacuum, or it can have 7 vacuums.
Okay.
So on the second sheet, it was just easy to say that there is always one special vacuum,
Yes.
and you compute in that. And we just hope that this is the minimum, that this is the lowest free energy vacuum.
Yeah, but yet you had to look at various Chern-Simons couplings and so on and so
No, but
forth.
these are just at that vacuum. These are in background fields like Hiroshi. Hiroshi has only background fields.
Yes.
So it's the same what we did.
Yes, but you had a more, seems to me, a more complicated effective action. You have all these
Oh,
Chern-Simons,
that's
and it
because-
only has this
Okay,
cosmological.
I'll explain that issue. But let's first start from the reduction on S1. You have a 3D theory, possibly many vacuum.
Okay.
On the first sheet, you might even get the gapless there, CFT of this 3D space. So, I mean, you cannot even say that it's a gap. So you cannot use even the high temperature expansion. This is what happens in bed theories.
Okay.
In some places, you might not even have vacuum in the 3D theory. So there might be some even other terrible things. But typically in ordinary QFT without supersymmetry, when you reduce the circle with anti-periodic boundary conditions, you have 3D theory, which has one trivial gap vacuum. It's trivially gap, no degeneracy. In that vacuum, there is, since it's gapped, it's just counter terms. You write down all the counter terms. It's an expansion in the size of the circle. If you want to get the leading order predictions for the density of local operators with spin, without spin, with flavor, you take the leading term in that in classical theory, because it's just pure background fields.
Okay.
And that's enough. In supersymmetry, even if there's just one vacuum, like on the second sheet in many cases, the term that Hiroshi wrote vanishes.
Oh, you're talking about Hiroshi's talk?
Yes.
Vanishes.
Yes, because n equals to supersymmetry in 3 dimensions forbids that counter term. This counter term is not compatible with it because it's a cosmological constant, so
Okay.
it's not terribly surprising.
Okay.
It's like writing a cosmological constant term in n equals to n equals to 3D,
Okay.
so it's not compatible.
I see. So
So the
that
leading
would be
term,
the leading term is
terms are
actually zero
Chern-Simons
for.
terms. Yes, so the leading term is actually a Ricci scalar, which Hiroshi never even discussed because it's subleading in the usual thermal effective field theory, high temperature effective field theory. And this Ricci scalar is like supersymmetrized with a bunch of Chern-Simons.
Okay.
So if you go beyond the leading order, there are like 3 or 4 terms, and that's why these papers on SUSY are a little more complicated. Because in the next order, there are 3 or 4 Chern-Simons terms, and you have to classify all of them to get the predictions correctly.
I see. So if this coefficient you're saying is 0, so it will actually be 0 on any manifold.
Yes,
So
it's
I
a
mean,
local
it's a
counter-term.
property of the.
Yes, so that's why this Cardi limit would works for the Schur index, for twisted index. I mean, it's like saying that, you know, if you do it super twisted index on.
But I mean, even on manifold that would break supersymmetry.
Yes. Yes, because it's as long as the S1 it's a property of the theory in R3, and then you can use it. The theory in R3 has n equals to SUSY. Then you can put it on any manifold you want. You
Okay.
calculate the counter terms in R3, and then just put them on curved space.
Okay.
So it gives you predictions for lots of different compactifications, not just superconformal index.
Yeah, but actually there is no prediction for supersymmetric theories, you're saying, no, because the coefficient is 0, so. For
In
supersymmetric
supersymmetric
theories,
theories,
you're saying you don't get any prediction.
No, you're reducing on an S1 with Hiroshi doesn't say how he reduces an S1.
Okay.
He assumes that the reduction in S1 leads to one trivially gapped vacuum.
And he writes this leading.
And then he writes this, and now, if you take a theory which is supersymmetric, if you reduce an S1 in just like the dumbest way with anti-periodic boundary conditions for spinors, of course, it will be one trivially gapped vacuum. So he would be correct. But if you reduce with the twist for the R symmetry, then there might be 17 vacuum.
Okay.
And each one of them will not have this counter term because of supersymmetry. So this counter term will vanish in those vacuum. So it's really a question of how you reduce an S1. People just assume that the usual reduction in S1 leads to one trivially gapped vacuum. It's just an assumption. You want to believe it, you believe it. You don't want to believe it, you don't.
Okay.
Even in QC, like or Yang-Mills theory, it doesn't lead to one vacuum because at small enough circles it breaks the one form symmetry, so it actually leads to n vacuum. But all of them have the same F, and this just contributes in some subleading order in the thermal expansion.
So if one would like to use this formula, for instance, to get the entropy of black holes, you're saying that
Not supersymmetry.
for non-supersymmetric black holes should work, but not for the supersymmetric ones.
Because the first supersymmetric ones, this counter term vanishes.
Yeah.
So you have to use the other formulas. Yes. Yeah, it will be a little more complicated for the supersymmetric black holes. I mean, it's not a question of whether the black holes are supersymmetric. It's more a question of what are the partition functions you're interested in with what is one boundary conditions. Like it's not really about which. It's more about the boundary conditions for spinors at infinity and ADS. You will get estimates for that partition function. Yeah, the supersymmetric formalism is much more complicated. without supersymmetry, almost everything is fixed by the leading term, which is the cosmological constant.
But then suppose that one, instead of putting the periodic boundary condition for fermions, one wants to compute thermal partition function. So you put the boundary conditions, break supersymmetry, and would allow for this contact term.
Yes.
And then you apply it to the charges of a supersymmetric black hole. So the black hole is supersymmetric, but you're not computing the index, right? You're computing the.
Well, I think now you're looking at you're computing a partition function in ADS5 with some boundary conditions, right? But I don't think these boundary conditions will be compatible with the supersymmetric black hole. Because I feel that it will not be able to fill the geometry with a supersymmetric black hole. Intuitively now there is temperature, like actual temperature. So the saddle point would be a non-extreme black hole. Right? Because you're just telling me which partition function you want to compute in filtering. That's well defined. But which saddle points fill it in the bulk. You're not going to find a BPS black hole anymore in these boundary conditions. I feel like that because it's a thermal partition function. It should be the ordinary ADS, large ADS black hole is temperature thing. I mean, that's what you get if you just do a normal thermal partition function of n equals 4 superannuals. You just get the large non-supersymmetric Schwarzschild black hole.
Okay.
That's the saddle point.
It's like it doesn't want to stick in when you're trying to put it away.
Yeah, I was more wondering.
I was actually just trying to put my own one, but then I realized that
Stop
was
leading
boundaries,
curves.
you know, like
Are important for
they're never
Kenichi.
exactly.
Maybe for some questions.
Okay.
It's not
Thank you.
obvious.
So it's down for forward.
Uh-huh.
Up for
Also,
back.
he had only one angular momentum, and I was
Awesome,
confused
thank you so
about
much.
it because actually there are two angular momenta. So I don't know.
So you mean depending on the dimensionality?
Yeah, I think Hiroshi did 3+1, right?
Ah, okay. I thought it was completely general.
No, but in 3+1 there are two angular momentum. We can try to classify operators by SO4 quantum numbers. So you
Yeah.
can take and ask about the density of operators as a function of two angular momentum. So I don't actually know what they did.
It looked like they had two parameters.
There were two angular momenta.
It looked like it to me.
I didn't see the slides. It was so small.
It was very small. It looked like to me that they had general angular.
Yeah. Yeah.
I still feel like the finicky details of that argument are probably not correct, but.
Yeah,
maybe-
but
it's true, but it's probably
small
true
point.
generically. Yeah,
It's a small point
Yeah.
in their argument.
yeah. No, I think it's true generically. It
I
just
mean,
more
he
like
just needs to rule out this delta equals 0. And somehow they cooked up some argument. It probably works in 99%
Yeah,
of the models.
my impression is that the answer is surely true generically. and
Yes,
Just
yes.
trying to understand sort of what
Yes,
that means.
yes. Yeah, and it seems like a very interesting question to me about that. So he was able to use this thermal effect. He was able to use thermal effect, this high temperature expansion to like estimate the number of the density of some representations. That's fine. But now you can do something a little bit more ambitious. Let's say you have a field theory in 4 dimensions with a U1 symmetry. And you have this main counter term, this F coefficient. Now, this F coefficient is a function of, let's promote it to be a function of theta, of mu, where mu is the chemical potential for the U1. Sure. Okay. And Hiroshi, all he needed was the expansion of F for small mu, like mu near 0, right? And that's enough to get all the results he wanted. But I would be interested to know if this function of mu is always minimized at mu equals pi. That's what's it. Let's say that mu is like a holonomy for a background gauge field.
Yeah.
I think if you look at simple examples, the free energy is like maximize at that equals pi. It's like Witten's free energy as a function of theta angle QCD. So it's always like gonna be. So Hiroshi made a comment that if you just expand this free energy around mu equals 0, it just drops a little bit. So the sign is fixed because it's a 2-point function of a current.
But that was the parameter B.
Yeah. You remember that he had a constraint about the second derivative. Around the origin.
B was positive and there was a minus B.
Yeah, and that's just because it's a question about 2-point function. In thermal
But
field
no, but
theory,
I
so
mean,
there's
the
positivity.
Probing it at general mu is much harder.
No, but yeah, that's why I said it's much more ambitious. A really good thing to try to prove would be that maybe it's a convex function, maybe it's maximized at theta equals pi. I feel it has to be true. I mean, it's a kind of a theorem about equations of states of matter.
Yeah, exactly.
That it's a complex chemical potential, so people don't have such things in the lab, but it's still a theorem about the equation of states for complex chemical potential. Maybe there is some way from anomalies to argue that maybe at theta equals pi it's not even differentiable, like in the Witten thingy. Like, I mean, I'm saying that maybe as you vary this chemical potential, some modes have to become massless at some value of this background chemical potential.
First order the transition, perhaps.
Yeah, exactly. And then there will be like a
but
cusp.
not second order. Perhaps,
Yeah, it could be
first
second
order.
or first order, and then there will be like a cusp singularity. In Witten's branches, there is this cusp.
Well, if you have an anomaly and you for the U1 symmetry, then you will definitely have some
Yes.
places where there'll be
Yes.
some massless.
Right, so, but so which anomaly for the U1 would guarantee that there must be a jump? You want to compactify with the chemical potential and argue that there is two vacua. So it has to be something like this coupling space anomaly.
Yeah, exactly. It descends from the, it can descend from the ordinary anomaly, but when you put the theory on the circle, the chemical potential, the imaginary part of the chemical potential is periodic and becomes like a new coupling space anomaly.
Yeah, I have some examples like that in 2+1D in a billion Higgs models with Ryan Thorngren. But I wanted like 3+1 in 3+1, like more realistic. Maybe some.
I mean, you can even do this for baryon number in QCD, and you can ask like whether.
I mean, nobody
you
proves
can prove
this in the
something.
experiment, but if you can put constraints on that part of the equation of state, it might be still useful.
Yeah.
So people only plot it for real mu, but
Yeah.
let's say there is the imaginary mu, and we have some constraints.
Yeah.
Maybe that leads to some global picture for the phase diagram. So yeah, I just wanted to know if there's some, maybe one can argue that it cannot be continuous in theta or not differentiable in theta. So say something.
Well, it's definitely true that there are special points in mu where it's not trivially gapped.
Yes. So I don't think this is, I think there are some examples like that in 2+1 at the moment, in my opinion.
Nobody did that for.
No.
Really? For.
I mean, in 2+1, it's very easy. Like the idea was that the chemical potential looks like a theta angle for the dimensionally reduced theory. And then you say, okay, with the theta angle, there has to be two vacua or it has to be gapless.
Yeah.
Now in 3+1,
I think.
how does it work? You have to you reduce
You
to
need
two.
some extra symmetry, like C
Yeah,
or
I'm not
CB.
sure how it works in 3+1. Which anomalies would guarantee that at mu equals pi, the 3D model is not trivially gapped?
I think that you will have an anomaly if you have just a standard cubic triangle anomaly for the U1 when you reduce it on the circle with chemical potential, that will become a anomaly in the space of coupling constants, mixing the reduced symmetry and the mu. And it's that. So I think they're just like direct translation.
I just haven't seen the argument. What I'm saying is that I think it's a good problem. In 2+1, there is a much more trivial argument that at mu equals pi, it cannot be trivially gapped because you reduce and it looks like a theta angle. Here you reduce, it doesn't look like a theta angle. It looks like some weird anomaly. So I don't know if one can say something about theta equals pi.
It won't be theta equals pi in general. That won't be, or mu equals pi. It would just be to say that as mu varies from 0 to 2 pi, there have to be some phase transitions.
Okay, I don't think this is in the literature, even for baryon symmetry in QCD. If one can really make it precise, I think it's interesting. And maybe with time reversal, you can even nail it down to some mu equals pi or something. It's more like a question about the global structure of these functions.
We just use the bathroom.
Yeah, I didn't understand how it works. And how this anomalies decoupling space actually work. I never understood it completely. How do you prove that there must be a phase transition? With some counter term jumps at some point. Do you think the U1 cubed anomaly would be enough to prove a coupling space anomaly?
Yeah, pretty sure of that.
Is the associativity true? Subtlety of associativity.
Because it would just be, that immediately just becomes like d mu wedge f wedge f.
So which counter term has to jump in the phase transition ADA, where A is the background field?
Yeah.
I see. So that suggests like a massless fermion as a phase transition.
And I think that's what, yeah.
That's what happens in free fermion theories. At final temperature, you just get the zero mode of mu
Exactly, yeah. And in like I even have some note about this with Daniel Brennan, but we never kind of pushed it to conclusion. But yeah, I would be happy to talk more about it.
Yeah.
You maybe write down, say what the.
It would be nice to understand, like we have the real slice of the QCD phase diagram.
If you
It'd
could
be
say
nice to
something.
understand how it extends to the cylinder.
Here is a thing which we can do.
On the other hand, on hand, so
So-
fixed anomaly when you give some touch configuration of CP.
Yeah, that might be.
So why I think about,
Yeah, that will specify.
if you look like it's a product, which with the loss of quality algebra, assume that you have
Operator corresponds.
certain S L.
That's what assures you, you're saying that the O will be too low.
Nice to try to do it.
I will explain.
Okay, on the same set. Which of these,
So in let's introduce the theory.
these are for the short.
Why?
Right? And then,
Why?
of course, that.
Why?
How would that be related to casting the potential?
So
Fermion, it won't be a cast, it will be like a massless fermion, so it will be a slightly non-differentiable function, right?
Okay.
It would be like second order phase transition, so it would be a jump in the second order.
Mhm.
If it just do vacuum, it's a jump in the counter term, it should look like a cast.
Yeah.
First order phase transition. In Witten, in what the Csaba
It
showed,
could be first order or second order.
Yeah, so
Right,
it's-
roughly Fermi.
yeah, in what Csaba showed, it was always like
Yeah.
this kind of thingy, so it's first order.
Yeah.
When he said that he found an example where it was continuous, I actually don't believe it contradicts this coupling system. He said that for an F equals AC, it's continuous, no branches. That cannot be right, because there has to be a phase transition.
What's the story about vanishing electron?
Well, I think I had some comments about your discussion and think that for an F equals C, you claim that there are no branches in the effective potentials and functions data.
Can F equals MC?
So it contradicts anomalies. It contradicts coupling space anomalies.
You're asking me if I have a nice categorization.
It might be that there is a point where the third derivative is not continuous. Second, that there is a massless particle. So there has to be something happening in at least one flight. That was one comment. That's what happens for an F equals one. For an F equals one, you don't have the cast. Usually you have this cast. The cast signifies two vacuums. And that's good because you need at least one phase transition.
Something makes sense because it's all built out of.
But for an F equals one, but there is a massless particle. So there is no two vacuum, it's a little different.
Why is there not?
If you do so,
For an F
if you see, if this.
For an F equals C, there is
One case.
yeah, it's an F equals and C case where you claim that there are no branches. So I'm saying it contradicts anomalies. There has to be something non-differential in your answer.
We just started computing. but even
Yeah, it could be that there is just a massless particle. So there is a discontinuity, it's like a higher order one.
No, I was just. generating.
It should be still branches.
We had not been able to.
But this is for the same principle. You can take.
So what's the
Information.
So you can't.
So
Now,
for
even
an
the algebra, even though most of them say
Because in the lightweight case, there's some.
that, you can see.
for an one, the matrix point
If
is not
you
special
write here, okay.
because there is not
I write
no
here,
practice
I will write.
for an f equals one. So if you just plot, so for an f equals one, let's say we just set the theta and push it to zero. And we plot the phase and we
These
plot
are
the
not
phases
integers,
of
but
the
some-
function of m.
Now,
M is a function.
some numbers.
We just then take the
Three vector
parameter
times.
and set the theta to zero without
It's,
another.
case of-
So
Yeah, right one.
in most places, there's one back.
Then
Most parts of the,
For example, there, the light.
but there is a special.
now let's try
a
and
special point here.
calculate.
The map.
If you start.
Special.
Say one,
There are two buttons.
this is the. Where? This is the metric data or. So in
So
principle.
the master thing the plan comes from some cancellation between the
Oh, this is not the.
implicit breaking and the.
And they just needed to insert.
There is one point with reflection of the axis. And line is two back, and in the rest of the diagram, the prime is massive and there is no.
Yeah.
It's just a phase diagram. of masses.
In other words.
So you're saying
Is that what eventually? It's on the other.
Yeah, because there's nothing, there's
Sides
nothing
insert
at
zero
zero.
operators, something
One
like
thing,
that.
it's not
Then
something
of
like.
course, if you- since it's
It
one.
depends.
I think that's right.
All you can say is that the phase diagram of the line, the lowest terminal.
One.
So all you can say, right?
Take four line operator.
And also for that, you can see the answer is that it's not compatible with anomalies.
Can you explain it again why?
All you know is that if it's not to be effective on the function theta, it's for a finite area, so discussing how many branches exist, is not simplifying. So what you really, and all you say is that this function is okay, differential. That's an anomaly. So
Interesting results.
like this.
Have you seen a lot of
It's not
examples of, you know,
physical
interaction versus non-interaction, the dual eyes?
I mean, other cases
Like other interaction, dual eyes.
looks like
It's a non-obedient case.
Yeah.
here the derivative.
Yeah, I know.
But it's not.
Again,
This thing, it's like a derivative. So we're shooting. But you can only the diagram for it.
It's in the paper already.
No, no, it's not. It's just, but.
So cannot be,
Zero, so
say, cannot be straight.
Implicit. I mean, I wrote this master.
Maybe true that.
I mean,
Just like the non-differential coefficient.
Yeah, maybe actually even application.
You were gonna say so.
And the
wow, that would be interesting. That would be interesting.
Yeah, I don't know.
You're right,
Yeah,
that's not why we do it. You're right, that's not why we do it, but it's.
Why do you say specific? Just kind of.
It's a fantastic.
But we found it for three separate.
I think the exact.
NC minus one. ST and NC.
Surely it can lead to some
NC minus one, we
application.
also.
And that's not the reason we do it. It's something like that.
Also, you could get three cases.
Just true.
Where we can see it.
Bro.
For small mass.
So. You can capture this, there is some.
Claim about anomalies.
Probably less. People do say such things anymore.
Yeah.
It's getting like borderline.
And you
can say you can send it to Japan, but they would not be sent a job because.
Right. So yes, so we all assume there's a part.
We discussed. The police says a few more.
It's not that it's not the same.
But it's simplifying. Almost done.
And then there's like.
I think there's also QCD-like, which are mostly for making fun of a nice way that like. Never.
Yeah, I meant. I always like to hear the word, like how much British was fantastic at the British TV. It's great. The best documentaries of whatever you can find. But in some respect, there are similarities between the cultures. There are also huge differences. Like the one similarity is the obedience. Very obedient, but even more than British. Germans.
Okay, sure, yeah, I'll be glad to.
In the Second World War, there were several attempts to assassinate Hitler, but there was no attempts to assassinate.
There were various assassination plots during that period, but they were on the other track.
Yes.
Yeah. I know.
Okay. Let us stop now. All right, thanks very much for the invitation. The title of my talk is Monopole, Quantum Numbers, and Anomalies. This is based on work that I published with Thomas Dumitrescu and Daniel Brennan. Fortunately, Thomas is not here. And of course, the subject of monopole quantum numbers is very rich and very well studied. And I won't be able to do justice to the older literature and references, but let me point out some of the key recent references which have thought about questions very similar to what I'll be talking about today. So let's start with some motivation. We're going to think about solitons and anomalies. And let me summarize our main results also. So we're going to describe a class of discrete Toft anomalies in 4D QFTs. We could study more generally other dimensions, but we'll focus on 4 dimensions. And we'll see that these kind of anomalies are closely related to the quantum numbers of line defects. For instance, their statistics, like whether they are bosonic or fermionic. We will have a practical method for computing these by studying fermion zero modes in a monopole background. So carefully studying the monopole Hilbert space. And so our basic picture for how to compute this class of anomalies, we'll start with some non-abelian gauge theory. We'll add, say, a Higgs field. We'll Higgs to a Coulomb phase. We'll do some calculations there, read off some subtle anomalies. And then if we like at the end, we could delete the Higgs field. It's just a crutch. And this kind of analysis naturally arises, for instance, in the Coulomb branch moduli space of 4D n equals 2 gauge theories, which is my unique mention of supersymmetry in this talk. But the big picture method works more generally. So you could say that we were inspired by that, but we're now just doing a sort of standard problem in quantum field theory. Okay, so what is there to say about Toft anomalies? So these are the simplest Toft anomalies that we all understand are for continuous global symmetries. Say U1 global symmetry, where we compute them by a one loop triangle diagram for free fermions. And these kind of anomalies, they're very easy to detect. For instance, that triangle diagram is telling us that the anomaly controls some power law piece of a current 3-point function. So they're detectable by correlation functions of local operators. That's therefore it's easy to see what we're talking about. And mathematically, we could say that they're characterized by an integer, which is like the sum of the cubes of the charges running over the loop. And you can think of this integer in an anomaly inflow way as it's an integer Chern-Simons level. Now, what about discrete anomalies, sometimes also called non-perturbative anomalies? One difference is that these are characterized by a finite abelian group. So the analog of the level in the inflow term is something discrete. And a kind of tricky part about them is that we can't really detect them with correlation functions of local operators. So it's harder to say what's the signal of the anomaly and what's the content of the fact that the anomaly is preserved under a normalization group flow. So this is kind of the motivating question here for this talk. So let's talk about an example of a non-perturbative discrete anomaly that everybody knows, which is Witten's SU2 anomaly. How does that work? We look at a theory with an SU2, say, global symmetry and n Weyl fermion doublets, and we're going to probe the theory with an SU2 background field A. I won't make A dynamical. It's not important for this discussion. Now, if we think of the theory on a space-time S4, the gauge transformations are parameterized by functions from S4 to SU2, which is S3. And since the fourth homotopy group of S3 is Z2, there exists some gauge transformations which are homotopically non-trivial. It's the original argument. And the partition function Z, thought of as a function of this background gauge field A, obeys this very simple equation, which is that if you do a gauge transformation with this homotopically non-trivial gauge transformation, you get a minus sign that's sensitive to n times the original partition function. And this sign in the gauge transformation rule is the anomaly. So it's a mod 2 phenomenon. That's what I mean when I said it was a discrete anomaly. Now, this is extremely abstract, that presentation. It's actually difficult to see what is the physical content of that anomaly, but Witten also answered that question in a later paper. So can we describe the physics of this anomaly more directly? And the idea here is you go to a phase where the SU2 symmetry is spontaneously broken. In that case, the anomaly remains, so we must be able to find it somehow. But now, since we've spontaneously broken this SU2 symmetry, the theory includes Goldstone modes, which are mapped from space-time to this group, SU2. And so there are solitons. And the soliton is a fermion if and only if the theory has the anomaly. That's the basic result. So that's very nice. It gives us a physical way to understand what this anomaly was, some way to detect it. Yes.
Really dumb question. So the Witten anomaly can't be realized by like some kind of West amino term when the symmetry is spontaneously broken?
Cannot be realized by some kind of West amino term. In a sense, I'm telling you about that West amino term.
Okay. There is.
But my recollection is that Witten characterized it at this as a time frequency. Discovered this anomaly that in some way it's the series inconsistent. So you cannot place, this fermion on, because about soliton, it's kind of another series.
Thank you for the question. So let me emphasize here that this SU2 symmetry is a global symmetry. If it's a global symmetry, then it's just it's not an inconsistency. It's just an 't Hooft anomaly like any other. Witten, when he wrote the paper, thought of SU2 there as being dynamical. Then it would be an inconsistency. But here we just think of SU2 as a global symmetry.
I said, what kind of soliton is there?
Skyrmion.
Skyrmion. SU2, okay, it's a global SU2.
In the gauge theory, the appearance of this anomaly shows up as a 1-0 mode.
That's another inconsistency. But that's when you think of the SU2 as a fluctuating gauge field. Yes. So
is it possible to understand the anomaly without deforming the theory at all?
Not in such a direct way, I think. So anyway, this is supposed to set up for a later discussion.
You kind of can. You can like gap fermions. You can try to add masses. But
I mean, so that's. You can detect, try to
but
detect.
you are saying that SU2, global SU2 is okay, right? So
it's okay. It's just a 't Hooft anomaly like any other, but a discrete one.
I see.
Okay, so our goal for the rest of the talk is we want to do something similar. We want to develop a physical dictionary of some class of discrete anomalies. And how will we do it? So we're going to do it by studying line defects and symmetry fractionalization. So I'll tell you about that for the next few minutes. Okay, so we'll focus for a while on lines in free Maxwell theories. We think of the lines as heavy probe particles. And we could think that such particles could be fermions or bosons. And typically when one says you're thinking about Maxwell theory, usually what you have in your head without saying more is that the Wilson line and the Topf line are both bosons. That's at least implicitly what you might be thinking if you didn't specify. And now if you fuse them, you get a dion with electric and magnetic charge 1 and 1. And that dion is a fermion. Because boson plus boson gives you boson, but there's some angular momentum from the electromagnetic field. So we have this fusion rule that we have the 2 bosons and then 1 fermion. And now if you think about, say, S-duality, we just heard a talk about SL2Z duality. More generally, you could choose any pair of these 3 basic charges to be bosons. So let's talk about how we could write an action for the other kind of non-standard choices. How would we think about the theory where the Topf line is a fermion, for instance?
It's in 4 dimensions.
We're all in 4 dimensions here, yeah. So one way to make this question transparent is to think about the theory on a curved manifold. In that case, a fermion should couple to the spin connection along its world line. We want to find that. And actually, more generally, we can do something else. We can even put the theory on a non-spin manifold. Maxwell theory is a bosonic theory, I think. So we're on a non-spin manifold, no spin connection even exists at all. And you could ask what happens to the fermionic lines. Now these fermionic lines, you think of them as the boundary of a topological surface. Yes, Peter.
I know that it works this way in Cyber-Witten theory, right? When you for the angular momentum, but are you claiming that it's always?
That's Dirac, yeah.
Just because of the Dirac.
That's just Dirac, yeah. Right, so this topological surface, you can think it's kind of analogous to Ramon sector operators in 2D CFT, where those operators are not exactly local operators. They have a topological branch cut that comes out from them. Same thing is happening if you have a fermionic line in Maxwell theory. If you place it on a generic manifold with no spin structure, it will have a topological surface coming out of it. So that's the picture. So this fermionic line, here's L. It's now the boundary of a topological surface sigma. And what's special about this surface is that we should have a world line action for this line that includes this coupling, an integral of over this manifold sigma of W2 of X. Here X is space-time, and W2 is the second Stiefel-Whitney class. Now, how did I know to write this? Well, one way is that if X is spin, then W2 of X is the derivative of the spin connection, you could think. So this is like, then you can pull this coupling back to the line, and it gives you the expected world line coupling for the fermions, the coupling to the spin connection. So this is the topological term that we need to have if we want L to be a fermion.
Just a question. So does it mean that the fermionic lines need to be at the boundary of a
surface?
What I mean, if you realize it by fusing 2 bosonic lines that don't need
There's a little surface in between them already. There's like a normal direction that came out of it.
Squeeze them, don't see.
No, but you remember the framing. This is like a way to say that you remember the framing. Okay, so now we know what we're hunting for. Let's make the Topf line into a fermion. How should we do it? So on a 2-sphere surrounding a Topf line, we have some magnetic flux. The integral of F is non-trivial. So I could produce the required coupling by including a new term in the action, which looks like F wedge W2 of X. Now, whenever F gets saturated, I'll have W2 in the transverse space. So this version of Maxwell theory where the Topf line is a fermion differs from ordinary Maxwell theory by its coupling to curvature and topology. We have some new explicit term in the Lagrangian. And you can do an analogous thing to make the Wilson line into a fermion. And for the cognoscenti, that's equivalent to making the dynamical field into a spin C gauge field. Something that also happens in Cyber-Witten theory. It's actually useful to view this procedure in terms of the underlying one-form symmetry of the Maxwell theory. So Maxwell theory has a U1,1 electric symmetry, whose charged objects are the Wilson lines, and a U1,1 magnetic symmetry, whose charged objects are the Topf lines. And there's an associated coupling to background fields, BE and BM, which looks like that up to some 2 pi's that I'm not writing. And you could say that the couplings that I've identified are just special cases of this coupling to background fields. Say if you want to make the 't Hooft line into a fermion, you just make BM into W2. That's a special case. You're allowed to turn on general BM. You can turn on this special BM. Now this is an example of what's called symmetry fractionalization, where you turn on backgrounds of one form symmetry, but those which are correlated with the underlying ordinary symmetry that you're trying to talk about. So here, this ordinary symmetry that we're trying to talk about is the space-time rotation symmetry. Now, there's another possibility. Instead of having two bosons in one fermion, it's actually consistent with the operator products to have all 3 of them be fermions. That's sometimes called all fermion electrodynamics. So it's consistent with because of the angular momentum in the electromagnetic field. And in this case, both BE and BM are W2. Now, there's an interesting phenomenon that occurs because of that. Namely, Maxwell theory has an anomaly when both its one-form symmetry backgrounds are on. This is the general anomaly. So this is an inflow term. Here, Y is a 5-manifold, whose boundary is our 4-dimensional space-time. And this is like a mixed Chern-Simons term, if you like. BE and BM are 2-form fields because we're talking about a 1-form symmetry. So this is a vanilla mixed Chern-Simons term. And if we want to talk about what's going on for all fermion electrodynamics, we should set both BE and BM equal to W2. And that leads to this anomaly for this all fermion electrodynamics. So here, what's happening, so W3 is the 3rd Stiefel-Whitney class, less familiar but to physicists, but nevertheless, Stiefel-Whitney classes come in a sequence, so we have to learn to deal with them. It's also a Z2 valued cohomology class. Now it's of degree 3. And so here we have a discrete gravitational anomaly. W3 is sort of morally like D of W2. That's why this formula works. And so this is a discrete gravitational anomaly. So this all fermion electrodynamics has a gravitational anomaly, but a discrete one, a Z2 valued one. Yeah.
I'm sorry, do you have like gapless fermions in this theory, or is this just this is pure gauge theory?
So maybe some of you grew up thinking that there were no gravitational anomalies in 4 space-time dimensions, but here's an example where we have a Z2 discrete gravitational anomaly just in 4 space-time dimensions.
Only for bosonic theories.
Only for bosonic theories, yeah. It's important to probe this anomaly. We have to be able to put the theory on a non-spin manifold. So it has to be a kind of theory where that's consistent, which means we don't have explicit fermion fields in the Lagrangian, for instance. No fermionic local operators in our theory. More questions? Okay, so that was an interesting story about all fermion electrodynamics and its gravitational anomaly. Let's now abstract from that some of the general rules about fractional charges of lines. So let's discuss coupling Maxwell theory to a general 0-form global symmetry group G. Could be part of space-time, like the SO4 rotations that we were talking about, or some internal flavor symmetry that we'll talk about later. And we'd like to ask the question, what quantum numbers are meaningful to assign to lines? What kind of answer can we give to what are the quantum numbers of line operators? And there's a naive answer. The naive answer comes when you say, well, a line is a heavy particle. Particles are in representations of global symmetry. Therefore, a line could be in a representation of a global symmetry. That is the naive answer, but that's the wrong answer. The reason that's the wrong answer is that we could dress our line by a counter term. So I could put on top of my line L some flavor Wilson line for any flavor symmetry I like. And that changes this representation that I just talking about. So we'd like to talk about properties of lines that are insensitive to this counter term. So we instead focus on quantum numbers that cannot be removed by these counter terms, and these are the fractional part of the charges of a line. So I'll explain a little bit more technically what that means. And so that's the key thing, is that it's the fractional part of the charge of the line that's robust. Yeah, Philip.
I'm confused by what counts as a counter term.
Just a functional of classical background fields. That's what I'm talking about. So for a classical, for a global symmetry G, there's some background connection, and I can just put stack L with a Wilson line for that background.
But line is not has ends or it's closed line.
You can think that it's closed line or it goes off to
No,
infinity.
because I'm asking because it could be something at the ends of the line, compensating fractional charge.
Good. So we'll see aspects of that actually later in the examples, but for now, just think it's closed. So we're just talking about the line part. Okay, so what are we talking about? What do we mean by fractional part of the charges? So if G is not simply connected, then there are non-trivial projective representations of the global symmetry group. And we'll talk about local operators. When we talk about local operators, we say that they're going to be non-projective representations of G. That's actually how I defined what G was. So I don't know what the symmetry G that I'm talking about is. I look at what is the faithfully acting global symmetry on local operators. That's what defines what G is in this problem. But even though the local operators are in ordinary representations of G, the line operators may be in projective representations of G. And this projectiveness is the fractional charge that I was talking about. This is the thing that's robust to counter terms. Right? The kind of flavor Wilson lines that I'm allowed to put are ordinary representations of G. And the fermionic lines are an example of this idea. Maxwell theory, all the local operators are bosonic, but the lines could be fermions. Now, it's not meaningful to ask for the exact numerical spin of the line, which half integer or integer it is, but it is meaningful to ask if it's integer or half integer.
The effective field theory is something. The full theory.
In the full, in some full UV description, it would be meaningful, but in, yeah. More questions? Okay, so that was a long story about quantum numbers of lines in Maxwell theory. And now we'd like to discuss some applications of that. Yeah.
Can I ask, so when they're all fermions, your way of detecting this is you have to put them on a non-spin manifold and calculate some partition function, see if you get a
For instance, yeah. That's one way. Okay, so, right, so our main interest is in the dynamics of interacting non-abelian gauge theories. It's nice to discuss something about Maxwell theory and get some details straight, but we like some applications to interacting theories. So we're going to start with some gauge theory with some fermions, and we'll have an adjoint Higgs field in our problem. And this adjoint Higgs field will condense and it will get to a Coulomb phase. And then we can apply the discussion that we just had. So we have an action schematically like this. Okay, so when you do that flow, you need to, if you want to detect these kind of discrete anomalies, you need to read off the quantum numbers of the lines result. How do we do it? Well, the Wilson lines are easy. They're going to just transform like the elementary fermions in this problem. Those are the objects carrying electric charge. And the Tuff line is more subtle. That's the quantum numbers of the monopole. So we need to study the monopole Hilbert space. And in general, if both the Wilson and the Tuff line, or the magnetic monopole and these fermions carry fractional charges under the global symmetry, this is a signal of a discrete anomaly. So this will be a calculational tool for detecting those. And of course, since it's a Tuff anomaly, it's present in all phases of the theory. So if you like, after you calculate it, you could even delete this scalar, and the anomaly is still there. Okay. So there's some technical thing that we need in order to actually achieve this flow. We need the fermions to be in pseudo-real representations so that we can have Yukawa couplings. But that still gives us lots of examples to play with. Let me start with the easiest one. So we'll start with an SU2 gauge theory with a Weyl fermion in a 2n dimensional representation. If n is odd, that's inconsistent because of the Witten anomaly, but if n is even, that's okay. So after Higgsing, we'll have Weyl fermion modes, which have electric charges Q, and these are the spectrum of Q. So it depends on the dimension of n, the dimension of this representation like that. And we're quantizing in the presence of a magnetic monopole here. So we want to, so for each electron of charge q, we'll find q real normalizable modes in the presence of a magnetic monopole of charge 1. And these are an irreducible representation of dimension q under rotation. So each of them is a full angular momentum multiple. Standard story. Okay, so we're going to quantize these modes to determine the statistics of the 't Hooft line. So simplest example that we could start with is a UV gauge theory with a single vial fermion in a 4. That's a consistent theory. And Higgsing gives an electron with charge, electric charge q equals 1 and q equals 3 in the presence of a magnetic monopole. And so we have a singlet under angular momentum and a triplet under angular momentum. And if we quantize that, we get 2 spinners of rotation. You could think of the singlet and triplet as being like the Pauli matrices, which are, so there are 4 of them, one's a singlet, one's a triplet. So SU2 gauge theory with a single fermion in the 4. So this monopole is therefore a fermion. That's the punchline of this discussion. And of course, the Wilson line, we're talking about a vial fermion in the 4 to start with, so the Wilson line is also a fermion. So what we concluded is that SU2 gauge theory with a single fermion in the 4 flows to this all fermion electrodynamics under this deformation, and so therefore has this discrete gravitational anomaly that we were talking about before. So this was first derived by Wang, Wen, and Witten. And more generally, this SU2 gauge theory with a single vial fermion in the 4R dimensional representation has an anomaly if R is odd. And if R is even, it does not, because the monopole will turn out to be a boson or fermion depending on the parity of R. It's still a boson. Yeah. Yeah, as long as this is even, it's boson theory. Any questions? Click.
Yep. If I also just added a bosonic heavy charge 1 or fundamental, let's say, then at low energies you would have like a bosonic charge 1 Wilson line in addition to this fermionic one. Is that true? But you just care that you can activate the anomaly at all.
Yeah.
Okay.
If you had the boson in the fundamental, the theory would not be bosonic anymore.
Yeah, that's true. Yeah.
So the
okay,
theory
sure.
would be a fermionic theory, and it wouldn't make sense to discuss.
Okay, yeah, thank you.
Okay, so let me talk about some richer examples to conclude. So we can compute many examples, but just to give you one, let's take SU2 gauge theory with 2 NF vial doublets. What's the symmetry carried by the local operators, the thing we call G in the previous discussion? So G is SO4 spin. The theory is bosonic because the local operators are all bosons. -1 to the F is part of the gauge group. And then there's an SO2NF mod Z2. So why SO instead of SU? It's because I have the adjoint scalar in the problem. So I have the adjoint scalar with the power coupling, so I have the SO global symmetry. We'll soon discuss what happens when we delete it. Okay, so this is kind of straightforward to analyze following the previous method. So the Wilson line.
So they say the theory is bosonic, but in the Lagrangian you have fermionic fields. So do you have to use some spin C gauge field?
It will be a spin SU2 gauge theory, gauge field. So the -1 to the F is part of the center of this SU2. So when you go to a non-spin manifold, you will be technically speaking in an SO3 1-null. But since SU2 is fluctuating, that's okay. Okay, so we analyze this as we did before. So the Wilson line, okay, it's a fermion that's fractionalized with respect to this, and it's also in a vector representation of SO2NF, which is fractionalized with respect to that Z2 quotient. So we have fractionalized both spin and flavor there on the electric charge. What about the monopole? Well, this is a famously studied example. The monopole is a boson and a chiral spinner of the flavor symmetry. So it's not fractionalized under the rotations, but it is fractionalized under the flavor symmetry. Okay, but anyway, we have simultaneous fractionalization of electric and magnetic degrees of freedom. So therefore, we should expect discrete anomalies, and we're going to find them. What's the formula? Okay, so the formula that you get, you can write it in two ways. So here, for simplicity, I've restricted myself to backgrounds of SO2NF, not mod Z2. There's a more complicated formula if you don't do that restriction, but just for the sake of presentation, we'll do this restriction. So the anomaly looks like this. You can kind of present it in two different ways. So it has a mixed space-time flavor presentation. And then there's actually a kind of tricky Steenrod equality that allows you to write that anomaly purely in terms of flavor if you wanted. So there's some relation among these kind of discrete anomalies that can be tricky to work out. Again, it's a Z2 anomaly. And okay, so that's the answer for this discrete anomaly. We get it by this method that I presented. You could ask what happens when the scalar is deleted. Maybe the scalar for you is just a crutch. You want to know what happens in the theory without the scalar. So first of all, the symmetry is enhanced. SO2NF goes to SU2NF. Right? We don't have the Yukawa couplings breaking the SU anymore. And then it's actually interesting that this discrete anomaly is a vestige of the perturbative chiral anomaly of the SU flavor symmetry. That's a little bit tricky to work out. The key equation is this one here. So the 6D inflow term for the chiral anomaly is a third Chern class. That's what descends to give the anomaly. You could ask what happens to this third Chern class if you restrict it to SO backgrounds, which is what will happen when you think of trying to match this. And your first instinct is that it goes exactly to 0. That's not exactly right. It has a torsion piece that's left over. That's what's appearing here. This W3 is the third integral Stiefel-Whitney class, and then you can do descent on this to get that. So, this anomaly that we found actually comes from the chiral anomaly in a tricky way. Okay, so I am out of time. So let me conclude with some open direction, some small scale open problems. To ask what other theories have these anomalies. We have kind of a calculational technique here. You can apply it to other examples. You could also generalize it in interesting ways. For instance, I talked about connected symmetry groups, but it's natural to ask also about, say, time reversal, where you would like to know if, say, a monopole is a Cramer's doublet or not, or maybe even something more fractionalized than that. And you could also ask, how do these anomalies manifest in various phases of theory? So what do they imply about chiral symmetry breaking phases, or other? How do you find them in other situations? And large scale, let me just come back to the motivation that I introduced at the beginning, which is that when we have this machine now in quantum field theory for producing lots of discrete anomalies, it's a kind of sophisticated cohomology apparatus, but it's hard to tell when a theory has those anomalies. And so it would be nice to have a general physical dictionary that tells you what is the most physical observable that will kind of the analog of the 3-point function of the current. So what should you do to detect a discrete anomaly? So this was one example of that. Okay, so I'll stop here and take more.
So just in the U1 case, if you broke the U1 down to like a discrete subgroup, is the anomaly still there, or is it? Because it wasn't like clear to me how the gapless modes are playing into this picture.
Good. So it's consistent with all the everything there to Higgs the U1 down to a Z2. So in order to preserve the spin charge relation that was kind of entering in that symmetry, I will need, say, a Higgs field of even charge. If I do that, then I'll get a minimal thing, would be a Z2 gauge theory, and that Z2 gauge theory can also have this anomaly. So it will match in that flow. So it's this kind of anomaly does not imply that a theory is gapless. So it can be realized by a gapped phase.
Very good. Thank you so much.
We'll come back in a minute.
So weren't you supposed to give a talk? No. Thomas was supposed to give a talk. Yes, but he's also an organizer. Hmm? Why don't you replace him?
Have to.
Why won't you give another one?
I can. So, das sie dann nicht stammt, so, so. Schnellste überlegen, was dann dabei.
We should okay, so
That one. Down. Go forward.
oh, okay.
And then you have a laser.
Thanks a lot. Okay, thank you very much, and thank you very much for inviting me to present some of the ideas on which we have been working in Theta recently. And in this occasion, I had the I thought that perhaps I should also discuss the relation between the result we have been obtaining in the last 5 or 6 years with what I have been doing in the context of supersymmetric gauge theories. And so this is a mixture of this, this talk is a mixture of kind of seminar about the last 5 or 6 years of our research work and some general ideas about the meaning of confinement in general. And what I think about the lessons which we can draw from the study of supersymmetric gauge series. So, so this is the plan. Just the idea of the work is as follows. I think understanding better the dynamics of strongly coupled chiral gauge series is a kind of challenge for all of us theorists. And the reason is, of course, you know that the standard model of fundamental interactions is essentially chiral gauge series. But this is a weakly coupled series and well understood in the context of perturbation theory. And nonetheless, in generally speaking, surprisingly little is known today about strongly coupled gauge series. Strongly coupled chiral. And it is in a striking contrast to the situation in vector-like gauge series like QCD, which we have learned many things, theoretical, experimental, and phenomenological results after 50 years of hard work by our community. And also, we should not forget about N=2 supersymmetric gauge series, which after the Seiberg-Witten revolution sort of solution of this class of gauge series, we have learned really many things, but they are all vector-like gauge series. So we decided at a certain point to study a class of chiral and SUN gauge, SUN just for complete, for definiteness. And we should perhaps generalize this study to SO, USP, but for the moment, let me limit to chiral SUN gauge series with Y fermions in different general reducible representation like this. And of course, these number of these fermions of each type must be such that the gauge anomaly should cancel. And for the sake of this talk, let me just call this kind of symmetric SUN fermions in symmetric tensor representation psi, anti-symmetric as a chi, and the fundamental anti-fundamental fermions as eta. And sometimes we also discuss about the adjoint fermion in adjoint representation, which I call lambda. Now, the request of asymptotic freedom limits ourselves to this. This is just two-dimensional subset of this space of models labeled by number of psi fermions and number of chi, so anti-symmetric. And some of them, and this is a sort of class of theories we are going to study, and some concrete examples of this. A class of chiral gauge series which have been studied for many years now are called Barzian-Kirovich models, and perhaps generalized Barzian-Kirovich models, which has fermions which are in the fundamental symmetric tensor representation psi, n+4 anti-fundamental fermion eta. These will be called Barzian-Kirovich. And these, of course, doesn't really matter, but just for the sake of discussion of this seminar, let me repeat that these will be called Barzian-Kirovich models, and or chi anti-symmetric representation like this, plus n-4 fundamental. And these will be called George-Gratiot models, or generalized George-Gratiot models if you add also vector-like pairs like this. So these will be called psi-eta model, this will be chi-eta model, or we also study this kind of model, one symmetric, one anti-antisymmetric tensor, and plus 8 anti-fundamental. And let me call this model Psi-Chi eta model or 1-1 model and so on. And we also study this kind of models or these. This is just QCD or adjoint QCD. Now, sorry. Yeah. So let me start with the highlight from our work between 18 and 23, and I will go through quickly five topics: Z2 anomaly, dynamical Higgs space, strong anomaly and phases, dynamical abelianization, and more general dynamical symmetry. Before going to complete the discussion of these topics, I have to quickly remind you that our works will be our discussion mainly depends on the idea of generalized symmetries developed by these people, starting from something like 2005. And the idea is to generalize this idea of symmetry from the traditional zero-form symmetry acting on local operators to K-form symmetries acting on line, surface, etc. operators. And the idea of, for instance, one-form symmetry is actually a familiar one from the idea of the center symmetry SUSY and Mills. And by using a Wilson loop or Polyakov loop, one, for instance, try to find the criteria for confinement or Higgs space and so on. But important news about new aspect about this development was to gauge this one-form discrete symmetry, for instance, discrete ZM symmetry. And the idea is to identify the field configurations connected to this one-form symmetry and identify them and kill the redundancies. So this is the idea of gauging this discrete ZM symmetry. And in order to do that, one introduces this field, B field. So one form BC and two form BC related by this essential factor N. And this means that the one is identifying gauge field configurations, those connected by ZN center transformations, and killing the redundancy. The net effect of this is to replace the topological density integral of instanton integral by a fractional number, which is given by essentially by fractional 1/n top fluxes. And one of the first striking results found by these people was that if you go to usual SUN and Mills and consider theta equal pi, turns out that the PP or T must be broken spontaneously if the vacuum has a mass gap. And so
I thought that they just proved that there was a discrete.
Pardon me?
I thought that they just proved that there was a discrete anomaly, so the vacuum cannot be trivially gapped.
Yeah, no, I mean, this is if the vacuum is not, it's trivial, then it should be so. And this result actually was known for many years. And
it does not prove that T must be spontaneously built.
Pardon me?
It does not prove that T must be spontaneously built.
This must not be
the existence of this discrete anomaly does not prove that T must be spontaneously broken.
If the theory is gapped, yes, because there's nothing which reproduces this anomaly unless the vacuum is degenerate. That's an idea, right?
it could be a deconfined DQFT.
Yeah, that's also possible. If it is confined and okay, it's trivial, then this is I agree on it. It's not a proof, but this is the kind of possible consequence. Let's say. Now, sorry. Yes. So our first result was Z2 anomaly. I don't know if this anomaly is related to what he was discussing, because I was listening to his seminar, but I'm not sure if it's related anyway. So all Bayesian Krovich and George Gratian models have actually a non-anomalous Z2 fermion parity symmetry. And this, of course, is part of Lorentz group, but this is another question which is not relevant here. Now, in a class of models with, for instance, even and psi-eta model, actually all Bayesian Krovich and George Gratian models with NP both even, this symmetry is a non-anomalous property of this symmetry is realized this way. If you go to compute to anomaly, you find the result. This is just chiral transformation. So you can go to compute the anomaly. You find that the result is that the integer instanton number plus angles, transformation angle, times non-vanishing even integer. And okay, it is not very well known that in these cases this non-anomalous Z2 symmetry is realized by this. And in fact, if you go to check the symmetry group space, you find out that actually before dividing some ZM symmetry which are in the intercept between SUN and this flavor group, this is flavor group in the case of psi-eta model. So there's just one U1 symmetry and this Z2 symmetry. Now, in other Bayesian Krovich and George Gratian models, with, for instance, psi-eta model with odd n, you see that there is no Z2 factor. And if you go to compute the anomaly, you get 0. And this is very similar to what you say that certain symmetry is non-anomalous because the fermion contribution just cancel out. And this is not so for this class of models. And now, in this class of models, gauging this one form color flavor locked ZM symmetry, which appear in this way, you find you do just a standard calculation, you get mixed anomaly, which is given by this. And this is a sort of kind of master formula we find later. And this is true for all Bayesian Krovich and George Gratian models with NPE. Now, in the infrared, you can check that massless baryons, which might have supported such a Z2 anomaly, does not. And let me check if convention of so one has to conclude that confining symmetric vacuum, which has been considered by a group of people, is actually inconsistent in this model. And in contrast, there is no problem in the Higgs space, as we see. Oh, this page is just to substantiate this, what I claimed, this master formula. In the case of psi-eta, you just consider first construct one form color flavor ZM symmetry, which is a combination of standard center ZM symmetry of the gauge group, under which, of course, fermions also transforms because center symmetry is by definition a kind of gauge transformations, and only the boundary condition after you going through the loop, complete loop, is non-trivial. physically transformed by Zn factor, extra Zn factor. And this is the reason why usually in the presence of fermion, in the fundamental representation, center symmetry is broken. But if there are non-anomalous U1 symmetries under which fermions transform this way, according to their charges, and if their charges are such that so as to cancel the center transformations, the nk is just annualities of each fermions. Then you can define color flavor of one form Zn center symmetry, and then you construct the gauging of such one symmetry, such Zn one form Zn symmetry, and then you construct gauge invariant kinetic terms, and after that you can just use, for instance, physical method to compute anomaly. And this is the result which I mentioned. Now, an objection to this argument has been presented by Tong et al. And they noted that the Z2 gauge field, which we have to introduce, this, here it is called A0. A0 must find this way because this is this gauge field represent the Z2 holonomy in defining this color flavor center symmetry. And A0 is necessarily singular somewhere inside in the closed two-dimensional surface surrounded by this loop. This is we are considering, for instance, bitorus-like space-time configuration. And now they proposed then that you have to use a regular Z2 gauge field, A0 like this, but then this BC, this one form gauge fields the flux become double, and then no Z2 symmetry appear. The problem of this argument is that this kind of configurations correspond to trivial Z2 holonomy, and therefore there are no transformation at all. So the fact that you don't find the anomaly for this trivial Z2 transformation is of course correct, but the significance of such a statement is not really clear. So to cure this problem, you can consider this psi-eta model with a regulator Dirac pair and singlet scalar phi with Yukawa interaction like this, and you assume that this scalar gets a vacuum expression variable B, which is much larger than the scale of psi-eta model. Then you see that below this scale V, the model reduces to the previously considered psi-eta model. However, in the ultraviolet, you have this kind of symmetry without Z2 symmetry. Now, Z2 symmetry, as you see from this picture, is actually a subgroup of U0. This is a non-anomalous continuous U1 symmetry. And this model, which we call X-ray model, in the ultraviolet, has a two non-anomalous U1 symmetry and the SUN. Okay, flavor SUN plus 4. Okay, this is also there. Now, this kind of structure can allow us to consider one form as Zn symmetry without any difficulty like this. And you go to construct the action gauge invariant, one form gauge invariant way, and you go to compute mixed anomaly. And you find this result. And especially this A0 BC to BC square anomaly reduces when the wave B is introduced to exactly to Z2 anomaly found before. Now, there's another, actually, there's another argument which strongly suggests that this confining vacuum with unbroken global symmetry with anomalies saturated by masses baryons only is not quite consistent, comes from the consideration of the so-called strong anomaly. Now, strong anomaly is something that, of course, everybody knows. It has been discussed this morning, so I'm not going to at all. But this was, for instance, known in QCD as a solution of so-called U1 problem. And people have written down this kind of effective low energy action. U is a standard sigma model field. And then you add this anomaly action. And this anomaly term will reproduce, be responsible for anomalous actual U1 transformation like this. Now, then you use the expansion of this U field like this, and then you see that this term precisely gives okay, taking into account of this and so on, it gives rise to theta mass and solve the U1 problem. Now, the question asked sometimes in this earlier works, what is, does multivariate logarithmic term make sense? And the answer is yes, because the U field is actually defined as an exponential expansion like this by definition. And then this is a perfectly well-defined action. Now, the idea is that to invert the logic, and this idea also appeared somewhere in this work, that if you take effective action, if you take this effective action for taking account of strong anomaly, now this implies that you must get a way to define this term in a well-defined way. Now, the idea is to apply the same logic in chiral gauge series, and we demand that low energy effective degrees of freedom be such that the low energy effective action with a strong anomaly term can be written in terms of them. So this is the idea. And for instance, in the Chi-eta model with fermion like this, strong anomaly effective action should have this term. Q is again FF and this logarithmic term must have argument like this. And this is dictated by the number of fermion thermals and the Toft effective action. You know that there must be this number of Chi's and this number of etas. It's just counting the fermion thermal. And therefore, one can, as in the case of U1 model of solution of U1 problem in QCD, one may argue that this kind of effective action does imply that the system is in a dynamical Higgs phase in which chi-eta, chi gets non-zero vacuum expectation value. I'll come to discuss about dynamical Higgs phase in the next page. So, on the contrary, confining chirally symmetric vacuum with massless baryons only as low energy degrees of freedom, this possibility fails this test because it is not possible to write down logarithmic this term, anomaly term, using this baryonic fields only. And the fact that it is impossible, you can see, okay, thank you, by just from fermion zero mode counting. And in the case with dynamical abelianization, there's no problem of this type. And so dynamical Higgs, this is not a problem because this Z2 anomaly is matched in the infrared by the fact that U1, C1, Ci-eta 1, hence the one from ZM symmetry itself is spontaneously broken. While for confining symmetric phase, this is a problem. This is a inconsistency. Okay, and another interesting scenario we discussed was dynamical reorganization. And actually, this study started with work which with Nisha. And actually, this was the work which sort of triggered our interest in all these chiral series. So let me just say that in this model, one of the few possibilities to realize this Toft anomaly matching, this conventional Toft matching anomaly, is to assume dynamical reorganization. And it is surprisingly difficult to find such a scenario if you try in all these chiral gauge theories I listed in the beginning. But anyway, so you assume the dynamical reorganization, the Toft anomaly matching is fine, sort of almost automatic. And then you go to check also the mixed anomalies. We did these computations. And the result is this certain continuous and discrete symmetries are broken by mixed anomalies. And this is perfectly matched with the assumption of dynamical sum.
How does the anomaly match in the Coulomb phase?
Yeah.
How does it match?
That doesn't matter.
I'm asking, how does it match?
How does it match?
Yes.
Well, I have somewhere table. It's essentially because eta phase SU8 symmetry remains unbroken, and the condensate is formed by chi and psi, and you see that since chi is antisymmetric, psi is symmetric. You see that the diagonal component of psi remains massless, eta all remain massless, and then total anomalies can be seen. And then we have been studying also more general dynamical symmetry, but I think I should skip because of time. In the class of model like this, you can consider several different dynamical symmetry breaking scenarios. This is sort of generalizing this dynamical organization, which we assumed to satisfy Toft anomaly mapping condition, and then we checked that the mixed anomalies confirm these consistencies and so on. So we are trying to generalize and trying to find other possibilities, especially in the case of SU5 model like this, with K-1. It's interesting because SU5 gauge symmetry is broken to SU2 plus U1 with something such beta function and so on. You know, we are just, this is just a trial which we are doing. And okay, it may be interesting to find some model in which this kind of things comes out. Okay, criteria of confinement. Okay, this I also go very quickly because everybody talks about confinement, but what is confinement really? No one seems to really know. We don't really understand what confinement means. So I just went through three well-known definitions. One is this old, most let's say naive definition like this. Particles with color cannot be freely propagating. The second is the Wilson loop, polygraph loop criteria, area row, no center broken, unbroken, and so on. Now this simulation seems to confirm that SUM pure Mills is in confinement phase. But the problem is that the pure Mills theory has nothing to be confined. So this, you know, this is the famous paradoxical situation. This is well-defined definition, but it works in a theory without anything to confine. And okay, this definition is also provided, but this I skip. And third definition is that confining as a dual superconductivity, dual Meissner effect. This is the idea of Toft. And okay, this is beautiful, and this everybody knows all these things. So if magnetic monopole condenses, then quark with this quantum. These are SU3. So there are two U1 charge, electric and magnetic charges. And you define Dirac unit between two particles, then you get something like this. And these are also fine, they're beautiful, but the definition C is also problematic because the idea involves abelian morphos. So you want to really, and this brings some difficulties. So maybe confinement is a sort of non-abelian dual Meissner effect. But then this brings different difficulties, which I will quickly go through with the supersymmetry models. But anyway, this is a very naive tentative criteria. You may just define different phases according to what sort of non-Goldstone bosons they produce. This is SUN color symmetry breaking, I'm saying, yeah. So the phase of an SUN gauge theory is not really determined by the underlying pure SUN theory, which is in confinement phase, between quotation marks, but by elementary, scalar, or composite, or solitonic condensates, and by the type of non-Goldstone boson they produce. And so this is a sort of idea which may be used. And
what does it mean to say you have a colored number Goldstone?
Excuse me?
What does it mean to say you have a colored number Goldstone boson? What does that mean?
Well, if you have a model and if you have, for instance, psi eta model, condenses psi eta, breaks SUN completely. So the N square minus 1 Goldstone boson are produced, but they are all absorbed by the gauge bosons. They become more massive, you know. So this is about really the fate of color gauge bosons. How many of them are fixed and become heavy? So these are very naive ideas, but maybe, you know, this can be applied to QCD. For instance, QCD is in confinement phase, perfect, because only condensates produce flavor number Goldstone boson, not color boson. So, okay, so I don't have time, so let me just very quickly, okay?
Just maybe questions now.
So I wanted to go through the idea of how all this super conformal. The idea is that confinement may be like close to non-abelian conformal fixed point, and of course this brings own difficulties because you know there are also non-abelian type of monopoles and ions all condensed together or appear, and then there's a lot of difficulties. But then the idea is somehow, and then this conformal fixed point is now deformed to confinement phase by some relevant deformation. This is the idea, no? And so how to study strongly coupled conformal infrared fixed point, which you don't know. And then there have been these development which could have helped us, Argus Zyberg, and especially this Guyot Zyberg Tachikawa Giacomelli duality, which allows us to study strongly coupled infrared fixed point of non-abelian type, where non-abelian monopoles and ions monopole quarks all appear as massless particles together. And then this has been used to study this deformation to confinement phase. And so this is last example of N equal 2, the superconformal fixed point appearing with the SUN gauge theory with NF equal to N minus 1, understanding like this. And what happens is that this superconformal fixed point is deformed by the joint mass, which brings N equal 2 to N equal 1 supersymmetry. The N equal 1 superconformal fixed point. This is the local theory of massless mesons in a joint representation. So it's really quite non-trivial result. And by deforming also by two masses, and this gives to confinement and flavor symmetry. So this is the last one. To sum up, supersymmetric gauge theories give us really deep insight and understanding on the quantum monopoles and ions and duality and everything, superconformal infrared fixed points. And they might give hints that confinement in QCD is somehow close to non-trivial conformal fixed point. However, deforming supersymmetric theories by supersymmetry breaking deformation, perturbation, is not easy, okay? If it is not impossible. And I think there are several reasons for this to be really a difficulty. The one is that supersymmetry is theories have quantum modular space or flat directions in general. So it is not clear at all where to start. And this is known by many people who tried to kind of work. And most important problem is that by fermion condensates like psi eta, chi eta, psi chi, or even by condensate in QCD, they all vanish by supersymmetry. It means that, in other words, interesting possible phases like dynamical peaks, Iberianization, even standard QCD are actually all out of reach out of supersymmetric cousins. So this is my conclusions. Maybe we should disappear, but maybe we should remember, keep in mind this beautiful word by Nambu. And with this, I stop. Sorry if I.
We want our question or lunch.
Did David Tong agree with your revised version?
Excuse me?
Did David Tong agree with your revised argument?
I don't think so. But if you read their paper, you will realize that their formula actually confirms what we are saying. Their formulas, not conclusion. You decide, everybody decide, you know.
One additional comment is that these theories we could study by using SUSY a little bit and perturb bracket by Anomaly. And it sort of confirms that global symmetry has to be proven.
Yes, this I noticed that your conclusion. But yeah, I don't know. I couldn't. I don't have really how you can avoid this kind of problem. You know, all these kind of fermion condensates are out of reach. That's in supersymmetric cousins, they are all zero.
But with perturbation, it can be nonzero.
No, this is true in the case. In some cases, you can put up like lambda condensate. That you can put up because this is lambda condensate is not forbidden by supersymmetry. But psi eta, psi chi, you know, chi eta, all these bifermion condensates are zero, punished by supersymmetry. It means that you have to break supersymmetry dynamically.
Yeah, they break it explicitly, and it's non-zero, but let's have this discussion afterwards. Okay.
What I was asking before about the I was thinking about just